There is a galaxy so large it could swallow our entire cosmic neighborhood and still have room left over. A single object containing 100 trillion stars, 5 times wider than the Milky Way, sitting at the heart of a galaxy cluster more than 1 billion light-years from Earth. For decades, astronomers pointed to IC 1101 as the largest galaxy ever found, a supergiant elliptical that redefined what the word galaxy could even mean. Its visible body stretches 550,000 light-years across. Its ghostly halo extends to 4 million light-years, wide enough to engulf the Milky Way, Andromeda, Triangulum, and every dwarf galaxy in between, without touching a single edge. It is a monument to cosmic scale, a structure so vast that our sense of distance quietly begins to fail. And then we found something bigger, not a galaxy with more stars, not a denser core or a brighter center, something else entirely. A pair of jets launched from a supermassive black hole stretching 23 million light-years across intergalactic space, longer than some cosmic voids are wide. A single object, powered by a single black hole, reaching across a distance so extreme that light takes 23 million years just to cross from one end to the other. Its name is Porphyrion, and it is not alone. Before Porphyrion, there was Alcyoneus. Before that, there were a dozen other radio galaxies whose scale made no sense. Structures so large they shouldn't exist in a universe this young, powered by physics we are only beginning to understand. So what happens when a galaxy grows so large that the old definitions stop working? What happens when the largest thing we've ever found gets dethroned by something we didn't even know to look for? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a kind of size that breaks your brain, not in a metaphorical way, not in the sense that it's impressive or hard to picture. I mean, it literally stops your ability to process scale. You can say the number out loud, you can write it down, you can nod along when someone explains it, but somewhere between your eyes and the part of your brain that handles spatial reasoning, the signal just dies. You end up with a fact sitting in your head like a stone you can't lift. Heavy, inert, refusing to mean anything. That's what happens when you try to think about IC 1101. It's a galaxy. That much is easy. Galaxies are familiar territory. We live in one. We've photographed thousands of them. We know what they look like, how they spin, how they're born and how they die. They're strange, sure, but they're not unknowable. You can fit a galaxy into your mental catalogue somewhere between a solar system and the observable universe. It has edges, it has a center, it's a thing. IC 1101 is also a thing. But it is so unreasonably, violently large that calling it a galaxy feels like calling the Pacific Ocean a puddle. Technically accurate, fundamentally misleading. Let's start with what we know for certain, because the numbers themselves are going to sound like a typo. IC 1101 sits at the center of a galaxy cluster called Abell 2029, roughly 1 billion light-years from Earth. It is the largest galaxy ever found in terms of its visible stellar body. Not the most massive, not the most luminous, not the one with the biggest black hole, though we'll get to that. The largest, the one that takes up the most physical space when you measure the region where stars are actually living and dying, the visible stellar core of IC 1101 stretches about 550,000 light-years from edge to edge, 500,000 light-years. That's the part we can see clearly in telescopes, the part where starlight is bright enough to register as a coherent structure, the part that looks like a galaxy in the traditional sense. For comparison, our Milky Way is about 100,000 light-years across. You could line up 5.5 Milky Ways side by side and still not span the width of IC 1101's visible body. And that's just the core. We're not even talking about the halo yet. We're not talking about the faint outer regions where the definition of the word edge starts to lose meaning. We're talking about the bright, dense, star-filled interior, the part that unambiguously belongs to the galaxy. Inside that region, there are approximately 100 trillion stars. 100 trillion. The Milky Way has somewhere between 200 and 400 billion, depending on whose count you trust. IC 1101 has 250 times more stars than our entire galaxy. If you wanted to visit every star in IC 1101 and spent exactly 1 second at each one, it would take you more than 3 million years. And that's assuming you could travel instantly between them, which you cannot, because they are separated by light years of empty space. Let's try a different angle because I'm not sure that number landed. Our Sun is one star. It has 8 planets, a few dozen moons, a belt of asteroids, a distant halo of comets. The entire solar system, everything gravitationally bound to our Sun, fits comfortably inside a bubble about 2 light-years across if you're generous with the definition. Most of the interesting stuff, the planets and moons we actually care about, sits within a few light hours. IC 1101 contains 100 trillion of those. 100 trillion suns, each potentially dragging along its own retinue of rocks and ice. If even a tiny fraction of those stars have planets, and current estimates suggest most stars do, then IC 1101 is host to trillions upon trillions of worlds. Some of them will be gas giants, some will be barren rocks, some will be ice balls in the outer dark, and some, statistically speaking, will sit in the narrow band of distance from their star, where liquid water can exist on a surface. We have no idea what's happening on those worlds. We can't see them. We can't image them. We can barely resolve individual stars in galaxies a tenth as far away as IC 1101, let alone pick out planets. But they're there, right now, orbiting stars whose light left home when Earth was still 1 billion years younger than it is today. Some of those worlds might have atmospheres, some might have oceans, some might have weather, tectonics, chemistry complicated enough to do interesting things, and all of it, every single star and planet and moon and asteroid, is locked inside a single gravitationally bound object that makes our galaxy look like a suburb. Here's where the brain starts to give up. If you placed IC 1101 where the Milky Way currently sits, its edges would stretch far beyond Andromeda. Andromeda, our nearest large galactic neighbor, sits about 2.5 million light-years away. It's the most distant object you can see with your naked eye on a clear night, a faint smudge in the constellation of the same name. The light you're seeing left Andromeda before humans evolved, before anything resembling a human walked upright, when our ancestors were still small mammals hiding in trees. Andromeda is unimaginably far away by human standards, and IC 1101 would swallow it whole without even reaching its outer suburbs. In fact, if IC 1101 replaced the Milky Way, it would engulf not just Andromeda, but most of the local group. The local group is the name for our galactic neighborhood, a collection of more than 50 galaxies loosely bound together by gravity. It includes the Milky Way, Andromeda, the Triangulum Galaxy, and a bunch of smaller dwarf galaxies scattered throughout a region about 10 million light-years across. IC 1101's visible core alone would dominate half that volume. Its outer halo, which we'll get to in the next chapter, would stretch even further. You would not be able to see the night sky the way we see it. There would be no Andromeda galaxy to point at. There would be no Magellanic Clouds, those two irregular dwarf galaxies that hover near the Milky Way's edge and are visible from the southern hemisphere. All of them would be inside, subsumed, part of the same colossal structure. The sky would be a wall of stars stretching in every direction, so dense and so bright that the concept of a dark night would not exist. That's the scale we're dealing with. And we're still only talking about the part we can see clearly. IC 1101 was discovered in the 1800s during one of the great photographic sky surveys that mapped the heavens on glass plates. It showed up as a faint, fuzzy blob, unremarkable except for the fact that it was very large and very faint. For decades, no one paid much attention. The universe was full of fuzzy blobs. Most of them turned out to be distant galaxies once telescopes got better. IC 1101 was catalogued, noted, and largely forgotten. Then, in the mid-20th century, astronomers began measuring distances to these objects using redshift, the stretching of light caused by the expansion of the universe itself. The further away something is, the faster it's moving away from us, and the more its light gets stretched toward the red end of the spectrum. IC 1101's redshift told a strange story. It was very far away, about 1 billion light-years, sitting at the gravitational heart of Abell 2029, one of the most massive galaxy clusters known. Galaxy clusters are exactly what they sound like. Hundreds or thousands of galaxies, all gravitationally bound together, orbiting a common center of mass. They're the largest structures in the universe that are held together by gravity rather than just drifting apart with the expansion of space. Abell 2029 is a giant even by cluster standards, and IC 1101 sits right in the middle, the heavyweight anchor around which everything else revolves. When astronomers measured IC 1101's size and tried to count its stars, the numbers didn't make sense. Galaxies weren't supposed to get that big. The standard models of galaxy formation, the ones that had worked perfectly well for everything else observed up to that point, said that galaxies grow through mergers. Two galaxies collide, their stars intermingle, their gas clouds smash together and ignite new rounds of star formation, and the result is a single larger galaxy. Repeat that process over billions of years, and you get the massive elliptical galaxies sitting at the centers of rich clusters. But IC 1101 wasn't just large, it was absurdly large. To build something that size, you'd need to merge dozens, maybe hundreds of galaxies together over the entire lifetime of the universe. And even then, the math was uncomfortable. Mergers are violent, they stir up gas, they trigger starbursts, they heat things up. IC 1101, by contrast, looked quiet, old. Its stars were predominantly red and yellow, the kind that form when a galaxy has run out of fresh gas and stopped making new stars. It wasn't a young, active, chaotic mess. It was a graveyard, a final resting place for stars that had been born elsewhere and dragged into the center of the cluster by gravity's slow, patient pull. That's the first thing that makes IC 1101 strange. It's not just big, it's old and quiet. Like a city that grew so large it ran out of building materials and now just sits there, vast and still, waiting. The second thing that makes it strange is where it sits. Hubble 2029 is not a random patch of sky. It's a dense, violent, crowded region of space where galaxies are constantly interacting, colliding, stripping gas from each other, and feeding the monsters at their centers. IC 1101 is the apex predator in that environment. It sits at the bottom of the cluster's gravitational well, the place where everything eventually falls. Over billions of years, smaller galaxies have drifted too close, been torn apart by tidal forces, and had their stars absorbed into IC 1101's growing bulk. This process is called galactic cannibalism, and it's how the largest galaxies grow. They don't form all at once. They don't collapse from a single cloud of gas. They eat. They wait at the center of a cluster and consume everything that wanders too close. And they do it slowly, over timescales so long that no human will ever watch it happen in real time. But the evidence is there in the structure. The faint streams of stars stretching out from IC 1101's core. The shells and ripples in its outer halo where smaller galaxies were shredded and digested. The sheer size of the thing, which can only be explained by billions of years of steady, relentless feeding. IC 1101 didn't build itself. It was built by gravity, piece by piece, corpse by corpse, over nearly the entire history of the universe. And here's the part that should bother you. That process is still happening. Right now, as you're reading this, IC 1101 is pulling in gas and stars from the cluster around it. It's growing, not quickly, not in any way you could measure over a human lifetime, but it is not finished. The galaxy you're looking at in a telescope today is not the final form. It's a snapshot of something still in motion, still feeding, still becoming larger, which raises an uncomfortable question. If IC 1101 is already the largest galaxy we've ever found, and it's still growing, where does it stop? What's the upper limit? Is there even a limit, or does it just keep eating until there's nothing left in the cluster to consume? We don't know. The models get fuzzy at these scales. Galaxy formation theory works beautifully for small and medium-sized galaxies. It struggles with the giants. There are too many variables, too many mergers to track, too many unknowns about how gas behaves in such extreme environments. IC 1101 is so far outside the normal range that it's less a data point and more a warning sign that the rules we thought we understood might only apply to a narrow slice of reality. The other uncomfortable part is the black hole. Every large galaxy has a supermassive black hole at its center. The Milky Way's black hole, Sagittarius A star, weighs about 4 million times the mass of the Sun. Andromeda's is bigger, somewhere around 100 million solar masses. Both of those are respectably large by galactic standards. IC 1101's black hole is estimated to weigh somewhere between 40 and 100 billion solar masses, 40 billion. The uncertainty in that number is larger than Andromeda's entire black hole. We're not even sure how something that heavy could have formed. Black holes grow by eating gas and stars, and there's a theoretical limit to how fast they can eat called the Eddington limit. Push past that, and the radiation pressure from infalling matter becomes so intense that it blows away the very material trying to fall in. A black hole that obeys the Eddington limit and starts from a stellar mass seed, say 10 or 20 times the mass of the Sun, should not be able to grow to 40 billion solar masses in the time the universe has existed, and yet there it is, sitting in the middle of IC 1101, silent, invisible, detectable only by the way the stars around it move. A monster inside a monster, and no one can fully explain how either one got so big. That's the setup. That's the object we're dealing with. A galaxy 5.5 times wider than the Milky Way, containing 100 trillion stars, anchored by a black hole heavier than anything the standard models allow, sitting at the center of one of the richest galaxy clusters in the observable universe, still growing, still feeding, still defying every comfortable assumption about how large things are allowed to get. And we've only talked about the part we can see clearly, because IC 1101 doesn't stop at its visible edge. It has a halo, a vast region of faint, diffuse starlight that extends far beyond the bright core. And depending on how you measure that halo, depending on where you decide the galaxy actually ends, the size estimates get even more unsettling. Some sources say the halo stretches out to 4 million light-years. Some say more. Some argue the question itself doesn't make sense because there's no sharp boundary, just stars fading gradually into the intergalactic void until you can't tell where the galaxy stops and the cluster begins. That's what we're stepping into next. The ghostly outer regions of IC 1101, where the definition of a galaxy starts to dissolve and the scale becomes something else entirely. We've spent time staring at the part of IC 1101 that behaves like a galaxy in the traditional sense, the bright core, the 500,000 light-year diameter sphere packed with 100 trillion stars, the part you can point a telescope at and say, yes, that is definitely a thing with edges and structure and a center. But we've been ignoring the part that matters more. Galaxies don't end where the starlight fades. That's a comforting fiction we tell ourselves because we need boundaries. We need to be able to say this is where the galaxy stops and space begins. But nature doesn't care about our need for clean definitions. And when you're dealing with something like IC 1101, sitting at the gravitational center of a massive galaxy cluster, the boundaries don't just blur. They dissolve completely. Every galaxy, including ours, has a halo. It's the vast, diffuse cloud of faint stars, gas, and dark matter that surrounds the bright central disk or ellipsoid we think of as the galaxy proper. The halo is where old stars go to retire. Globular clusters, those ancient spherical swarms of stars that formed in the galaxy's youth, live out here. So do streams of stars ripped from smaller galaxies that wandered too close and got shredded by tidal forces. The halo is the graveyard, the attic, the junk drawer of a galaxy. Everything that doesn't fit in the main structure ends up here, drifting in slow, wide orbits around the core. The Milky Way's halo extends out to maybe 200,000 light-years. Maybe more if you count the outermost globular clusters and the faint wisps of gas detected at extreme distances. It's big, it's mostly empty, and it contains only about 1% of the galaxy's total stellar mass. The real action, the part we care about, the part with spiral arms and star-forming regions and planets and life, sits in the disk. The halo is background noise. IC 1101's halo is not background noise. It is the dominant feature. Depending on how you measure it, the halo extends somewhere between 2 and 3 million light-years from the core. Some sources push that estimate even higher, to 4 or even 6 million light-years, though at that scale, the definition of where the galaxy ends and the surrounding cluster begins gets philosophical. What everyone agrees on is that the halo is absurdly, unreasonably large. Larger than the visible body of the galaxy by a factor of 4 or more. Larger than anything else we've measured around any other galaxy. Let's use the conservative number, 2 million light-years from the core. That gives IC 1101 a total diameter, core plus halo, of about 4 million light-years. 4 million light-years from one side to the other. To put that in perspective, the entire local group, the collection of more than 50 galaxies that includes the Milky Way, Andromeda, Triangulum, and all the dwarf galaxies orbiting them, spans roughly 10 million light-years. IC 1101's halo alone takes up 40% of that volume. If you dropped IC 1101 into our neighborhood, its halo would extend past Andromeda, past Triangulum, past the Magellanic Clouds, and well into the space occupied by the more distant dwarf galaxies scattered throughout the group. You wouldn't just swallow Andromeda, you'd swallow the space between us and Andromeda. The 2.5 million light-year gap that currently separates the Milky Way and our nearest large neighbor would sit comfortably inside IC 1101's halo. The collision between the Milky Way and Andromeda, which is expected to begin in about 4 billion years, would be happening inside a single galaxy's outer suburbs. That's the scale of the halo. Not twice as big as the visible core, not 3 times, 10 times, maybe more. And it's not empty, it's full of stars. Faint ones, old ones, stars so dim and so spread out that detecting them individually is nearly impossible from Earth. But they're there, billions of them, maybe trillions. No one has counted because no one can. The halo is too diffuse, the stars too faint, the distances too extreme. What we can detect is the light from the halo as a whole. When you take a long exposure image of IC 1101, the core shows up as a bright blob. The halo shows up as a faint glow surrounding it, fading gradually into the background until it becomes indistinguishable from the noise in the detector. Measuring where that glow actually stops is like trying to measure where the edge of a fog bank is. You can define an arbitrary cutoff, some threshold of brightness below which you decide the galaxy has ended, but it's not a real boundary, it's just the point where your instrument gives up. The halo isn't just old stars, it's also where most of the galaxy's dark matter lives. Dark matter is the invisible stuff that makes up about 85% of the matter in the universe. It doesn't emit light. It doesn't absorb light. It doesn't interact with anything except gravity. We know it's there because galaxies rotate faster than they should based on the visible mass alone. The stars on the outer edges of a galaxy should be moving slowly, the way the outer planets in our solar system take longer to orbit the Sun. Instead, they move just as fast as the stars near the center. The only way that works is if there's a huge amount of invisible mass spread throughout and around the galaxy, pulling everything along with it. In the case of IC 1101, the dark matter halo is staggeringly massive. Estimates vary, but the total mass of the galaxy, including dark matter, is somewhere in the range of tens of trillions of solar masses, maybe as high as 100 trillion. That's the mass of 100 trillion suns, spread out over a volume 4 million light-years across. Most of that mass is dark matter. The stars, all 100 trillion of them, are just the visible tip of a much larger gravitational structure. That dark matter halo is what holds the galaxy together. Without it, the stars in the outer regions would drift away. The core would still be bound by its own gravity, but the diffuse outer halo, where stars are separated by hundreds or thousands of light-years, would evaporate. The fact that IC 1101 has held onto its halo for billions of years tells us the dark matter is doing its job. It's the scaffolding. The stars are just the decoration. Here's where it gets stranger. The halo isn't a static thing. It's constantly changing. Every time a smaller galaxy falls into a Bell 2029 and drifts too close to IC 1101, it gets torn apart. The stars don't all fall into the core immediately. Most of them get scattered into wide, chaotic orbits around the galaxy, becoming part of the halo. Over time, those orbits settle down. The stars spread out, and what was once a distinct small galaxy becomes an indistinguishable part of the larger structure. Astronomers can sometimes see the evidence of recent meals: faint streams of stars arcing through the halo, shells of material rippling outward from the core, clumps of stars that haven't fully mixed into the background yet. These are the remnants of smaller galaxies that IC 1101 consumed in the last few billion years. The process is slow. A galaxy doesn't get shredded and absorbed in a single violent event. It takes hundreds of millions of years, maybe longer. The smaller galaxy makes pass after pass through the outer regions of IC 1101, losing a little more of itself each time, until eventually there's nothing left but a faint trail of stars marking where it used to be. This is galactic cannibalism, and it's how IC 1101 grew to its current size. The galaxy wasn't born this large. It started as something much smaller, maybe a normal large elliptical galaxy, sitting at the center of a forming galaxy cluster. Over billions of years, gravity did its work. Smaller galaxies drifted inward, collided, merged, and fed the growing giant at the center. The core got denser, the halo got larger, and the process repeated over and over until what we see today is less a single galaxy and more a graveyard of hundreds of smaller ones. The halo is the evidence. It's where the corpses are buried. Every star out there, every faint globular cluster, every wisp of gas used to belong to something else. IC 1101 didn't create those stars. It inherited them, and it's still inheriting more. That raises an uncomfortable question. If the halo is full of stars from other galaxies, at what point does it stop being a halo and start being the cluster itself? Where do you draw the line between IC 1101 and Abell 2029? The galaxy sits at the center of the cluster, and its gravity dominates the region, but the cluster is full of other galaxies, hundreds of them, all orbiting the same center of mass. Some of those galaxies are close to IC 1101, close enough that their halos might overlap, close enough that stars could drift from one galaxy's halo into another's without ever crossing a meaningful boundary. This is the problem with defining the size of a galaxy like IC 1101. The visible core is straightforward. You can see where the stars are densely packed and where they start to thin out. But the halo doesn't have a clean edge, it just fades. And at some distance, what you're looking at isn't really IC 1101's halo anymore. It's the intra-cluster medium, the diffused sea of stars and gas that fills the space between galaxies in a cluster. The boundary between the two is arbitrary. It's wherever we decide to stop calling it a galaxy and start calling it a cluster. Some astronomers argue that the 4 million light-year number is meaningless for exactly this reason. They say IC 1101's true size is closer to the visible core, maybe 600,000 or 700,000 light-years if you're being generous. The rest, they say, is just cluster material that happens to be near the galaxy. It's not gravitationally bound to IC 1101 in any meaningful way. It's just passing through. Other astronomers disagree. They point out that IC 1101's gravity dominates the region. Stars in the halo, even the faint ones millions of light-years from the core, are in orbit around the galaxy. They're not drifting freely, they're bound. And if they're bound, they're part of the galaxy, whether we like it or not. The fact that we can't see a sharp edge doesn't mean the edge isn't there. It just means the edge is defined by gravity rather than starlight. Both sides have a point, and the truth is probably somewhere in the middle. IC 101 is both a galaxy and something larger, a hybrid object that doesn't fit neatly into the categories we've built to describe these things. It's the central galaxy of a cluster, a type of object called a CD galaxy, where the C stands for supergiant and the D refers to the extended diffuse halo. CD galaxies are rare. They only form in the most massive clusters, and they only exist because they've spent billions of years sitting at the bottom of a gravitational well, slowly consuming everything around them. IC 1101 is the most extreme example we've found. Other CD galaxies have halos. None of them have halos like this. None of them stretch across 4 million light-years. None of them contain enough stars to build dozens of Milky Ways and still have material left over. Here's what that means in practical terms. If you were somehow standing on a planet orbiting a star in IC 1101's halo, 2 million light-years from the core, you would still be inside the galaxy. You would look up at the sky and see the faint glow of the core, a distant smudge of light so far away that even at the speed of light, it would take 2 million years to reach you. The stars around you would be sparse. Your nearest neighbor might be 100 light-years away, maybe more. The space between stars in the halo is so vast that you could live your entire life without ever seeing another star up close. But you would still feel the galaxy's gravity. Your star would be in orbit around the core, moving at hundreds of kilometers per second, completing one orbit every few billion years. You would be part of the structure, a single star in a halo of trillions, drifting through the dark, bound to a core you could barely see. And here's the strangest part. You wouldn't be alone. The halo is full of stars like yours. Faint, old, widely separated. Most of them are red dwarfs, small stars that burn slowly and can live for trillions of years. Some of them are white dwarfs, the cooling remnants of stars that exhausted their fuel billions of years ago. A few are globular clusters, dense swarms of ancient stars that formed in the early universe and have been orbiting the galaxy ever since. If any of those stars have planets, and some of them almost certainly do, then there are worlds in IC 1101's halo, worlds orbiting stars so far from the galactic core that the concept of a galaxy might not even occur to anyone living there. They would see a mostly empty sky, a few faint points of light scattered across the darkness, maybe a distant glow on the horizon if they looked in the right direction, but no Milky Way, no band of stars stretching across the sky, just emptiness. And yet they would be inside one of the largest galaxies in the universe. They just wouldn't know it. The halo also contains something else, something we can't see directly but know must be there. Primordial gas. Hydrogen and helium left over from the Big Bang, drifting through the space between stars, too diffuse to collapse into anything but still present. In a normal galaxy, this gas would have been used up long ago, converted into stars or blown away by supernovae and stellar winds. But in a galaxy as large as IC 1101, sitting in the middle of a cluster as rich as Abell 2029, the halo acts as a reservoir. It holds on to gas that would otherwise escape. Not enough to form new stars. The gas is too hot and too spread out for that, but enough to add mass, enough to keep the halo fed. That gas is part of the intracluster medium, the hot ionized plasma that fills the space between galaxies in a cluster. It's heated to millions of degrees by the gravitational energy of the cluster itself. We can detect it with X-ray telescopes because gas that hot emits X-rays, and when you map the X-ray emission from Abell 2029, you see a vast glowing cloud centered on IC 1101, extending far beyond the galaxy's visible edge. That cloud is where the halo blends into the cluster. It's where the galaxy stops being a discrete object and becomes part of something larger. And it's a reminder that at these scales, the idea of a galaxy as a separate, self-contained thing is misleading. IC 1101 is part of Abell 2029. It shaped the cluster shaped it. The two are inseparable. And that's what makes the halo so important. It's not just an extended region of faint stars, it's the interface between the galaxy and the environment it lives in. It's where material from the cluster gets absorbed. It's where smaller galaxies get torn apart. It's where the gravitational influence of IC 1101 reaches out and touches the rest of the universe. Without the halo, IC 1101 would just be a very large elliptical galaxy. Impressive but comprehensible. With the halo, it becomes something else, a structure so large it challenges the definition of what a galaxy is. A gravitational anchor for an entire cluster. A monument to the slow, patient process of cosmic cannibalism that has been happening for most of the universe's history, and it's still growing. The halo is still pulling in material. Stars are still being stripped from smaller galaxies and scattered into wide orbits. Gas is still falling in from the intra-cluster medium. The process is slow, almost imperceptibly slow, but it hasn't stopped. IC 1101 today is larger than IC 1101 a billion years ago, and IC 1101 a billion years from now will be larger still. So when you see a headline that says IC 1101 is 4 million light-years across, understand what that number represents. It's not just the galaxy. It's the galaxy plus its graveyard, the core plus the corpses, the visible structure plus the invisible scaffolding of dark matter holding it all together. It's a measurement of influence as much as size. A way of saying this is how far IC 1101's gravity reaches before the rest of the universe takes over. And that reach is staggering. 4 million light-years, 40% of the local group's volume, a region so large that light takes 4 million years to cross it. A halo so diffuse that most of it will never be mapped in detail, never be fully understood, never be anything more than a faint glow in a telescope's detector. But it's there, right now, wrapped around 100 trillion stars, holding together the largest galaxy we've ever found, and quietly, patiently continuing to grow. So how did IC 1101 get this way? What sequence of events leads to a galaxy this massive, this extended, this absurdly large? That's not a question about halos anymore. That's a question about history, about the violent, chaotic process that builds giants, about the architecture of cosmic monsters and the forces that sculpt them over billions of years. So how does a galaxy end up this large? That's the question that should have been bothering you since the moment you heard the numbers. 100 trillion stars, 4 million light-years across, a mass equivalent to tens of trillions of suns. These are not the dimensions of a normal galaxy. These are not even the dimensions of a large galaxy. These are the dimensions of something that broke the rules and kept growing long after it should have stopped. IC 1101 didn't start this way. Nothing in the universe starts fully formed. Galaxies are built over time through a process that's equal parts construction and demolition. They grow by eating each other, by colliding, merging, ripping each other apart, and reassembling the pieces into something larger. It's a violent process that happens on timescales so long that no human will ever watch it unfold in real time, but the evidence is written into the structure of every massive galaxy we've ever observed. And IC 1101 is the most dramatic example of what happens when that process runs for billions of years in exactly the right environment. The story starts with galaxy mergers. Not the gentle, orderly kind where two spirals waltz together and blend smoothly into a new disk. The chaotic kind. The kind where two massive galaxies slam into each other at hundreds of kilometers per second, their stars passing through each other like ghosts because space is so empty that direct collisions between individual stars are almost impossible. What collides instead is the gas. The enormous clouds of hydrogen and helium drifting through each galaxy get compressed, heated, ignited. Star formation explodes. Entire regions of both galaxies light up with newborn stars, bright blue and short-lived, burning through their fuel in a few million years and dying in supernova blasts that seed the surrounding gas with heavy elements. The merger takes hundreds of millions of years, maybe a billion. The two galaxies don't just touch once and combine. They pass through each other, their gravitational fields pulling and stretching, creating long tidal tails of stars and gas that stream out into space like ribbons. Then they swing back around, pass through again, lose more orbital energy and repeat. Each pass pulls the two cores closer together. Each pass strips more material from the outer regions and scatters it into chaotic orbits. Eventually the cores merge. The supermassive black holes at the centers of both galaxies spiral inward, radiating gravitational waves and coalesce into a single larger black hole. The stars from both galaxies mix. The gas either gets used up in star formation or gets blown out by feedback from the merged black hole. And what's left is an elliptical galaxy. That's the standard story for how ellipticals form. You take two spiral galaxies, smash them together, and the result is a smooth, featureless blob of old stars with no disk, no spiral arms, and no ongoing star formation. The violence of the merger destroys the delicate structures that define a spiral. The orbits of the stars get randomized. What was once an organized, rotating disk becomes a swarm of stars moving in every direction at once, held together only by their mutual gravity. IC 1101 is an elliptical, a giant elliptical, which means it didn't form from a single merger. It formed from dozens, maybe hundreds. Every merger added mass. Every merger brought in new stars, new gas, a new supermassive black hole to feed the growing monster at the center. And every merger left behind evidence in the form of faint shells and streams of stars in the outer halo, the remnants of smaller galaxies that got shredded and absorbed. This process is called hierarchical merging, and it's the backbone of modern galaxy formation theory. Small galaxies form first in the early universe, built from the collapse of primordial gas clouds in regions where dark matter had already clumped together. Those small galaxies collide and merge into medium-sized galaxies. Medium-sized galaxies collide and merge into large galaxies. Large galaxies collide and merge into giants, and the process continues for as long as gravity keeps pulling things together. In most regions of the universe, the process slows down after a few billion years. Galaxies spread out. The expansion of space carries them away from each other. Mergers become rarer. Galaxies settle into their final forms and spend the rest of cosmic history slowly aging, converting their remaining gas into stars, and eventually fading as the star formation rate drops to zero. But IC 1101 didn't form in most regions of the universe. It formed in the center of a galaxy cluster, and that changes everything. Abell 2029 is one of the richest galaxy clusters known. It contains thousands of galaxies, all gravitationally bound together, all orbiting a common center of mass. The cluster itself is about 600 million light-years across, though most of the galaxies are concentrated in a much smaller region near the core. And at the very center of that core sits IC 1101. Galaxy clusters are the largest gravitationally bound structures in the universe. They're the endpoints of cosmic structure formation, the places where the universe's matter has been pulled together by gravity into the densest configurations possible. And the centers of clusters are special. They're where the gravitational potential is deepest, where the density of galaxies is highest, where the collision rate is fastest, and where the largest galaxies in the universe grow by a process astronomers call galactic cannibalism. Here's how it works. Imagine you're a small galaxy drifting through the outer regions of a cluster. You're moving at high speed, maybe 1,000 kilometers per second, but so is everything else. The cluster is full of galaxies, all moving in different directions, all held together by the combined gravity of the entire system. Most of the time, you pass by other galaxies without incident. Space is mostly empty. Even in a dense cluster core, the galaxies are separated by hundreds of thousands or millions of light-years, but every so often you pass close to another galaxy, close enough that your mutual gravity starts to matter. If the other galaxy is roughly the same size as you might merge, a violent, chaotic collision that takes 1 billion years to complete and leaves behind a single larger elliptical. But if the other galaxy is much larger, something different happens. You don't merge, you get torn apart. The tidal forces from the larger galaxy's gravity pull harder on the side of you that's closer to it than the side that's farther away. That difference in pull stretches you. Stars and gas on your leading edge get pulled away. Stars on your trailing edge lag behind. Your galaxy becomes a stream. A long, thin ribbon of stars and gas, stretching across hundreds of thousands of light-years, marking the path you took through the larger galaxy's gravitational field. Over the course of many passes, you lose more and more material. Your core shrinks. Your outer stars are scattered into orbits around the larger galaxy, becoming part of its halo. Eventually, there's nothing left of you as a distinct object. You've been absorbed, cannibalized. Your stars are now part of the larger galaxy's population. Your gas, if you had any, has either been stripped away or mixed into the larger galaxy's reserves, and your supermassive black hole has spiraled into the core and merged with the central black hole, adding a few million or billion solar masses to its already enormous bulk. This is what happened to IC 1101 over and over. For billions of years, it sits at the bottom of Abell 2029's gravitational well, the place where everything eventually falls. Smaller galaxies drift inward, get torn apart, and feed the growing giant. The process is called dynamical friction. As a galaxy moves through the cluster, it interacts gravitationally with all the other galaxies and the dark matter surrounding them. Each interaction saps a tiny bit of the galaxy's orbital energy. Over time, those tiny losses add up. The galaxy's orbit decays, it spirals inward, and eventually it reaches the core, where IC 1101 is waiting. IC 1101 is what astronomers call a CD galaxy. The C stands for supergiant. The D refers to the diffuse extended envelope of faint stars surrounding the core. CD galaxies are rare. They only form in the most massive clusters, and they only form at the center. They're the result of billions of years of cannibalism, hundreds of smaller galaxies consumed over cosmic time, and they're some of the most massive single objects in the universe. The fact that IC 1101 is a CD galaxy tells us its history even if we can't watch that history unfold. It tells us that it formed early, when the cluster itself was still assembling. It tells us that it sat at the center of the forming cluster and grew by accreting everything that fell inward. And it tells us that the growth process hasn't stopped. IC 1101 is still the dominant gravitational force in Abell 2029. Smaller galaxies are still falling in. The halo is still expanding. The process is slower now than it was a few billion years ago because most of the nearby galaxies have already been consumed. But it's not finished. Here's the uncomfortable part. If you could watch IC 1101's growth in fast forward, starting from the early universe and running all the way to the present, you'd see a monster being born in slow motion. A small elliptical galaxy sitting at the center of a forming cluster, surrounded by dozens of smaller galaxies. Over the first few billion years, those smaller galaxies collide and merge, building up the central object. The cluster grows. More galaxies fall in from the surrounding cosmic web. Some merge with each other. Some fall all the way to the center and get absorbed by the growing giant. The central galaxy gets larger, its halo expands, its black hole grows, and the process repeats. By the time the universe is 10 billion years old, IC 1101 has already consumed dozens of galaxies. It's massive, old, and running out of gas. The mergers have used up most of the available fuel for star formation. What's left is a population of old red and yellow stars, slowly aging, with no new generation to replace them. The galaxy has stopped making stars. It's become a graveyard, a monument to the violence that built it. And then it keeps growing. Because even though the star formation has stopped, the cannibalism hasn't. Smaller galaxies keep falling in. Their stars get added to the halo. Their black holes get added to the core. The galaxy gets larger and more massive, but it doesn't get brighter, it just gets more diffuse, more spread out. The halo expands to 2 million light-years, then 3, then 4, and the process continues. That's the story of IC 1101. It's a story of patience, of gravity doing its slow, relentless work over timescales longer than the lifespan of most stars. It's a story written in the structure of the halo, in the faint shells and streams of stars left behind by galaxies that no longer exist. And it's a story that's still being written today. But there's another part of the story that matters just as much: the black hole. Every massive galaxy has a supermassive black hole at its center, and there's a tight correlation between the mass of the black hole and the mass of the galaxy's central bulge. Bigger galaxies have bigger black holes. The relationship is so tight that astronomers use it as a tool to estimate black hole masses in distant galaxies where we can't measure them directly. IC 1101's black hole is estimated to weigh somewhere between 40 and 100 billion solar masses. 40 billion. That's 1,000 times more massive than the black hole at the center of the Milky Way. It's one of the largest black holes ever measured, though the uncertainty in the measurement is large enough that we can't say for sure whether it's the largest. What we can say is that it's enormous, and that it got that way through the same process that built the galaxy. Mergers. Every time IC 1101 absorbed a smaller galaxy, it also absorbed that galaxy's black hole. Two supermassive black holes, each weighing millions or billions of solar masses, spiraling inward over hundreds of millions of years, radiating gravitational waves, and eventually colliding. The result is a single larger black hole, and the process repeats. Dozens of mergers, dozens of black hole coalescences, each one adding mass to the growing monster at the center. The black hole's growth had a side effect, a critical one. It's part of the reason IC 1101 stopped forming stars. When a supermassive black hole feeds, it doesn't do so quietly. Gas falling inward gets heated to millions of degrees by friction and compression. That hot gas emits radiation, lots of it. X-rays, ultraviolet light, jets of high-energy particles that stream out along the black hole's rotation axis at nearly the speed of light. Those jets plow into the surrounding gas, heating it, stirring it, and in some cases blowing it out of the galaxy entirely. This process is called feedback, and it's one of the most important mechanisms in galaxy evolution. Without feedback, galaxies like IC 1101 would keep forming stars for much longer than they actually do. The gas in the halo would cool, fall into the core, and ignite new rounds of star formation. But feedback prevents that. The black hole heats the gas, keeping it too hot to collapse. The jets blow bubbles in the intracluster medium, pushing gas away from the core and out into the space between galaxies, and the result is a galaxy that has run out of fuel, not because the fuel was used up, but because it was prevented from cooling down. IC 1101's black hole has been doing this for billions of years. Every time the galaxy absorbed a smaller system, fresh gas fell inward, the black hole fed, and the feedback kicked in. The jets heated the surrounding medium, the star formation slowed, and eventually it stopped almost entirely. What we see today is a galaxy that's effectively dead, old stars, no new stars, and a black hole sitting quietly at the center, waiting for the next meal. This is the fate of all giant ellipticals. They grow through mergers, they build up massive black holes. The black holes suppress star formation through feedback, and the galaxies age into red, dead systems that will eventually fade over trillions of years as their stars die one by one and nothing replaces them. But IC 1101's story doesn't end there, because while it's one of the largest galaxies by stellar extent, it's not the largest structure we've found, not even close. The next chapter in this story isn't about stars at all. It's about something far stranger, something that doesn't show up in visible light, something that stretches across distances so vast that IC 1101's 4 million light-year halo starts to look modest by comparison. It's about radio galaxies, jets of plasma launched by supermassive black holes, carving through the intergalactic medium and inflating enormous lobes of radio-emitting gas. Structures that dwarf even the largest stellar galaxies. And in the last few years, astronomers have found examples that push the definition of a galaxy to its breaking point. Objects so large that calling them galaxies feels inadequate. Objects that force us to reconsider what we mean when we talk about the largest things in the universe. IC 1101 held the title of largest galaxy for decades. It's about to lose it. Not because we found a bigger stellar galaxy, though there are competitors, but because we found something else entirely. Something that makes IC 1101 look like a warm-up act. We've been talking about galaxies as though they're dead things, frozen structures, collections of stars bound together by gravity, aging slowly over billions of years, their stories already written, and for most galaxies that's close enough to the truth. They form, they evolve, they merge, and eventually they settle into a final configuration that will last for the rest of cosmic time. The stars slowly die. The black hole at the center sits quietly, waiting for the occasional snack. Nothing dramatic happens, nothing that would make you look twice, but some galaxies never got the memo. Some of them have black holes that refuse to stay quiet. Black holes that are feeding right now, actively, violently, on enormous quantities of gas and dust. And when a supermassive black hole feeds, it doesn't just grow larger. It becomes the loudest, brightest, most energetically ridiculous object in the universe. It becomes what astronomers call an active galactic nucleus, an AGN. And the structures those objects create make IC 1101's halo look like a footnote. This is where the scale breaks in a different direction. We've been measuring galaxies by how many stars they contain and how far those stars extend from the core. That's a reasonable way to define size if you're talking about stellar populations. But when you start talking about AGN, the stars stop being the thing that matters. The black hole becomes the story. And the structures it creates, the jets and lobes of plasma it launches into space, can extend to distances that have nothing to do with where the stars are. Distances that make IC 1101's 4 million light-year halo look modest. This is the part where we stop talking about the largest galaxy and start talking about the largest structures made by galaxies, because those are not the same thing, and the difference is everything. Let's start with the black hole. We've mentioned it a few times already. Every large galaxy has a supermassive black hole at its center. The Milky Way weighs about 4 million solar masses. IC 1101's weighs somewhere between 40 and 100 billion. These are objects so massive and so dense that their gravity warps space itself. Get too close and nothing, not even light, can escape. Cross the event horizon and you're gone. You're not destroyed in any normal sense. You're removed from the universe. You fall inward forever, and no information about what happened to you can ever get back out. Most of the time, these black holes sit quietly. They're not feeding, there's no gas nearby, or if there is, it's too hot and moving too fast to fall in. The black hole just sits there, a gravitational anchor at the center of the galaxy, doing nothing. From the outside, you wouldn't even know it was there, except for the way the nearby stars move. Their orbits get faster and tighter the closer they get to the center. Measure those orbits carefully and you can infer that there's something enormously massive sitting in the middle, something that doesn't emit any light. That's how we found Sagittarius A star, the black hole at the center of our own galaxy. We watched stars orbit an invisible point for more than 20 years and calculated the mass of whatever they were orbiting. 4 million suns packed into a region smaller than the orbit of Mercury. Now imagine the same black hole, but this time there's gas nearby. A lot of gas. Maybe the galaxy recently merged with another galaxy and the collision funneled huge amounts of gas into the core. Maybe a star wandered too close and got torn apart by tidal forces, its shredded remains falling inward in a thin stream. Maybe the galaxy sits in a dense region of a cluster where gas from the intracluster medium is slowly raining down onto the core. However it happens, gas starts to fall toward the black hole. It doesn't fall straight in. If it did, nothing interesting would happen. The gas would just disappear across the event horizon, and that would be the end of the story. But gas has angular momentum. It's moving sideways as well as inward, and as it falls, conservation of angular momentum forces it into a tight spiral, the same way water swirls as it goes down a drain. That spiral becomes a disk, a flat, rotating structure called an accretion disk, where gas is slowly losing energy and spiraling inward toward the black hole. The accretion disk is where the magic happens. As the gas spirals inward, it rubs against itself. Friction heats it up. The closer it gets to the black hole, the faster it's moving and the hotter it gets. By the time the gas reaches the innermost stable orbit, the last place it can exist before falling across the event horizon, it's heated to millions of degrees. Gas that hot doesn't glow red or white. It glows in X-rays. It becomes one of the brightest sources of radiation in the universe. A quasar, if the black hole is massive enough and the accretion rate is high enough, A single feeding black hole can outshine every star in its host galaxy combined by a factor of 100, by a factor of 1,000. The black hole itself is invisible, but the disk around it is so bright that we can see it from billions of light years away. And then there are the jets. This is the part that still makes physicists uncomfortable because the details are not fully understood. Somehow, in a process that involves the rotation of the black hole, the magnetic fields threading through the accretion disk, and the enormous energy density near the event horizon, a fraction of the infalling material gets redirected. Instead of falling into the black hole, it gets funneled into two narrow beams that shoot out perpendicular to the disk along the black hole's rotation axis at speeds close to the speed of light, 99% the speed of light, 99.9% in some cases. These are called relativistic jets, and they are the most energetically absurd things a galaxy can produce. The jets are not made of gas in the normal sense. They're plasma, ionized particles, mostly electrons and protons, stripped of their electrons and accelerated to speeds where relativistic effects matter. Time dilation, length contraction, the whole suite of weird consequences that show up when you start moving close to the speed of light. The particles in the jet are carrying enormous amounts of kinetic energy, and they're all moving in the same direction, a tightly collimated beam that can stay focused for millions of light years before it starts to spread out. Think about that for a second. A beam of plasma launched from a region smaller than our solar system, traveling in a straight line for millions of light years without dispersing. The amount of energy required to sustain that is staggering. The amount of organization required to keep the beam collimated over those distances defies easy explanation. And yet the universe is full of these things, thousands of them, maybe tens of thousands. Wherever there's a supermassive black hole feeding at a high rate, there's a good chance it's launching jets. The jets don't travel through empty space. They plow into the intergalactic medium, the thin soup of gas that fills the space between galaxies. That gas is already hot, a few million degrees in a typical galaxy cluster, heated by the gravitational energy of the cluster itself. But the jets are hotter and faster, and they carry so much momentum that they push the intergalactic gas out of the way, carving tunnels through it. The displaced gas piles up at the edges of the tunnel, forming enormous bubbles called radio lobes. The lobes are filled with the jet material, plasma, that's still glowing, still radiating energy, though by the time it's spread out into a lobe, it's cooled down enough that it's no longer emitting X-rays. Instead, it emits radio waves, long wavelength radiation that we can detect with radio telescopes. That's what a radio galaxy is, a galaxy with jets, a galaxy whose central black hole is feeding and launching relativistic outflows that inflate enormous lobes of radio-emitting plasma on either side of the core. The galaxy itself, the stars and the gas and the dust, sits in the middle. The jets shoot out perpendicular to the galactic disk, and the lobes grow at the ends of the jets, sometimes stretching to distances far larger than the galaxy that produced them. The lobes are not solid, they're diffuse clouds of plasma, magnetic fields and high-energy particles, but they're real. They have mass, they contain energy, and they're part of the structure the galaxy created, even if they're not gravitationally bound to it in any meaningful way. When we talk about the size of a radio galaxy, we're talking about the distance from one lobe to the other measured through the core. That's the structure's extent. And for the most powerful radio galaxies, that extent can be enormous, millions of light years, tens of millions in extreme cases. Radio galaxies have been known since the 1940s, when astronomers started building the first radio telescopes and scanning the sky for sources of radio emission. They found that some galaxies, particularly large ellipticals, emitted far more radio waves than could be explained by their stars. Follow-up observations with better instruments revealed the lobes, two bright blobs of radio emission sitting on either side of the galaxy, often symmetrically placed, connected by fainter jets that traced back to the core. For decades, radio galaxies were a curiosity. Interesting, sure, important for understanding the physics of black holes and jets, but not something that fundamentally changed the conversation about the largest structures in the universe. The biggest known radio galaxies had lobes that stretched a few million light-years, large but not dramatically larger than the halos of giant ellipticals like IC 1101. The stars were still winning the size competition. Then telescopes got better, surveys got deeper, and in the last few years astronomers have found radio galaxies so large that they force a rethinking of what the word structure even means at cosmic scales. Here's the problem with detecting very large radio galaxies. The lobes are diffuse. The radio emission is spread out over an enormous area, which means the surface brightness, the amount of emission per unit area, is very low. Low enough that it's easy to miss if you're not looking carefully. Early radio surveys used relatively small dishes with limited sensitivity. They could detect bright, compact sources, but faint, extended structures often fell below the detection threshold. It wasn't that the structures weren't there, it's that the instruments couldn't see them. Modern radio telescopes changed that. Instruments like the low-frequency array, LOFAR, a network of radio dishes spread across Europe that work together as a single enormous telescope, can detect faint diffuse emission that earlier instruments missed. LOFAR observes at low frequencies, which is exactly where the emission from old, cool radio lobes is strongest. And in the last few years, LOFAR surveys have been turning up enormous radio galaxies that no one knew existed. Structures so large that the galaxies producing them look like tiny dots sitting in the middle of vast clouds of plasma. The energy budget for these objects is absurd. To inflate a radio lobe millions of light-years across, you need to pump an enormous amount of energy into the intergalactic medium. And you need to do it over a long period of time, tens of millions of years, maybe 100 million. The jets don't turn on and off instantly. They run, steadily, for geologic timescales. The black hole at the center keeps feeding, the jets keep launching plasma, and the lobes keep growing. Eventually, the black hole runs out of fuel. The jets shut down. The lobes start to fade as the plasma cools and loses energy. But while the jets are running, they're doing work on a scale that dwarfs anything happening in the galaxy's stellar population. Let's put some numbers on this. A typical large radio galaxy might have lobes that extend a few 100,000 light-years from the core. That's already impressive. The lobes are larger than the galaxy, but the energy required to inflate them is within the range of what a moderately active black hole can provide over a few tens of millions of years. The black hole feeds at a few percent of the Eddington limit, the maximum rate at which a black hole can accrete matter without blowing itself apart with radiation pressure. The jets carry away a fraction of that energy. The lobes grow. Everything makes sense. Now scale that up. Imagine a radio galaxy with lobes that extend not a few 100,000 light-years, but a few million, or 10 million, or more. The energy required scales with the volume of the lobes. Bigger lobes mean more plasma, more magnetic field energy, more work done against the pressure of the intergalactic medium. To power a structure that large, the black hole needs to feed at a very high rate for a very long time, and the jets need to stay collimated over distances where even tiny perturbations should cause them to spread out and lose focus. That's what makes the largest radio galaxies so strange. They shouldn't exist. or rather they should be rare. The conditions required to produce them, a massive black hole, a long-lived supply of fuel, a stable jet that doesn't wobble or precess, and an environment where the intergalactic medium is dense enough to confine the lobes but not so dense that it chokes off the jets. All of that needs to line up perfectly, and yet we keep finding them, which suggests either the conditions are less rare than we thought, or the physics of jet propagation is more forgiving than the models predict. One more thing before we get to the specific objects. The lobes are not static, they're dynamic. The jets are constantly pumping new plasma into them, pushing against the intergalactic gas, inflating the lobes like balloons. As the lobes expand, they compress the surrounding gas, creating shock waves that ripple outward. Those shock waves heat the gas even further, to tens of millions of degrees, and that heated gas emits X-rays. So when you observe a radio galaxy with both radio and X-ray telescopes, you see a complex layered structure, the radio lobes marking where the jet material has gone, the X-ray emission marking where the lobes are interacting with the surrounding medium, and sitting in the middle, invisible in both radio and X-rays, the galaxy itself, the stars, the gas, the black hole, the thing that started all of this. Radio galaxies are important for more than just their size. They're probes of the intergalactic medium, the way the jets propagate, the shape of the lobes, the spectrum of the radio emission. All of that tells you about the environment the jet is moving through. How dense is the gas? How hot is it? How magnetized? These are questions that are hard to answer by looking at the gas directly because it's so diffuse and faint. But the jets leave tracks, they disturb the gas, they light it up. And by studying the disturbance, you can learn about the medium. They're also probes of black hole activity over cosmic time. Every radio galaxy you see is a snapshot of a black hole in the middle of a feeding event. The jets are running now, or they were running recently, and the lobes haven't faded yet. By counting how many radio galaxies there are at different distances, which translates to different times in the universe's history, you can build a picture of how often supermassive black holes turn on, how long they stay active, and how much energy they inject into their surroundings. That energy matters. It's part of the feedback process we talked about earlier. The jets heat the intergalactic medium, preventing it from cooling and falling into galaxies to form stars. In the densest regions of galaxy clusters, where the gas should be cooling rapidly and triggering massive starbursts, the jets from the central radio galaxy keep the gas hot and prevent the cooling. They regulate star formation on scales much larger than the galaxy itself. So when we find a radio galaxy with lobes stretching 10 or 15 or 20 million light-years, we're not just finding a big structure, we're finding evidence of a black hole that shaped the evolution of an enormous volume of space. A single object, sitting at the center of a single galaxy, influencing the temperature, density, and star formation rate of the intergalactic medium across distances that span multiple galaxy clusters. That's the power of a relativistic jet. That's the scale at which AGN feedback operates. And that's why radio galaxies matter. For a long time, the largest known radio galaxy was an object called 3C236. The name comes from the third Cambridge Catalogue of Radio Sources, a survey conducted in the 1950s and 60s that catalogued thousands of radio-emitting objects across the sky. 3C236 was entry number 236. When astronomers measured its lobes, they found a structure about 15 million light-years across. 15 million, that's 3 times the diameter of IC 1101's halo. The galaxy producing 3C236 is a relatively ordinary elliptical, a few 100,000 light-years across, but its jets carved out a structure 30 times larger. 3C236 held the record for decades. It was the standard example used in textbooks to illustrate the maximum size a radio galaxy could reach, and then LO4 came online and started finding larger ones, not just one, several. Structures that pushed the scale up to 16 million light-years, then 17, then beyond. The problem with defining the largest radio galaxy is the same problem we had with defining the size of IC 1101's halo. Where do you decide the structure ends? The lobes are diffuse. They fade gradually into the background. There's no sharp edge. You can define a cutoff based on some threshold of surface brightness, but that cutoff is arbitrary. Use a more sensitive telescope, and you might detect emission extending even further. Use a less sensitive one, and the structure looks smaller. So when you see a claim that a particular radio galaxy is the largest ever found, what's really being said is that it's the largest structure detected above a certain sensitivity threshold with a certain instrument. That's not a criticism, that's just how observational astronomy works. You measure what you can measure and you report it. But the fact that we keep finding larger examples as instruments improve suggests we haven't hit the upper limit yet. There are probably radio galaxies out there with lobes extending 20 million light-years, maybe 25, maybe more. We just haven't detected them yet because they're too faint, or because we haven't surveyed the right patch of sky with the right instrument. Every time someone builds a more sensitive radio telescope and points it at a deep field, new giants show up. And every time, the definition of what counts as large gets pushed a little further. That's the landscape we're stepping into. A regime where the size of a galaxy is no longer defined by stars, where the structures we're measuring are not bound by gravity, where the extent is determined not by how far the galaxy's mass reaches, but by how far its black hole's influence extends. IC 1101 is enormous. 100 trillion stars, 4 million light-years across. A monument to the slow accumulation of mass over billions of years. But the structures we're about to discuss make IC 1101 look like a warm-up act. Because the largest objects in the universe are not galaxies. They're the shadows galaxies cast into the intergalactic medium. The scars left behind by black holes that refuse to stay quiet. And the scale of those scars is about to shatter every comfortable assumption we've been carrying about how large things are allowed to get. In 2022, a team of astronomers announced the discovery of a radio galaxy unlike anything seen before. A structure so large it redefined what the word galaxy could mean. A single object, powered by a single black hole, extending across a distance that makes IC 1101's halo look like a suburb. Its name is Alcyoneus. And it is where this conversation about scale stops being academic and starts being unsettling. In 2022, astronomers using the low-frequency array, LO4, were scanning deep radio surveys of the northern sky when they found something that should not have been possible. A structure so large that when they first calculated its extent, several members of the team assumed there had been an error in the data processing. There had not been an error. The structure was real. And it was about to force a very uncomfortable conversation about what the word galaxy actually means. They named it Alcyoneus, after the giant from Greek mythology who fought against the gods during the war between the Titans and the Olympians. The name is appropriate. This is not a galaxy in the sense that most people understand the term. It is a monster, a single object, powered by a single supermassive black hole, extending across a distance of roughly 16 million light-years from one end to the other. 16 million. That's 4 times the diameter of IC 1101's halo. That's more than 160 times the diameter of the Milky Way. That's a distance so large that light, traveling at 186,000 miles per second, takes 16 million years to cross it. Let me put that in a context that might land better. The local group, the collection of galaxies that includes the Milky Way, Andromeda, Triangulum, and all the dwarf galaxies orbiting them, spans about 10 million light-years. Alcyoneus is larger than that. If you placed Alcyoneus where the Milky Way sits, one of its lobes would extend past Andromeda, past Triangulum, out beyond the edge of the local group entirely, and into the space between galaxy groups. The other lobe would stretch in the opposite direction, past the Magellanic Clouds, past every dwarf galaxy in our neighborhood, reaching into a region of space so empty and so far from anything familiar that we have no common reference points for it. And this is a single structure, one galaxy, one black hole. One set of jets carving a scar across the universe so large that it defies every intuitive sense of scale the human brain is capable of holding. Alcyoneus was not hiding. It was sitting in plain view the entire time. The problem was that no one had looked at it with the right instrument. The host galaxy, a relatively unremarkable elliptical with the catalogue designation SDSS J081421.68 plus 5224110.0, sits in the constellation Lynx, about 3.5 billion light-years from Earth. In optical light, it looks like thousands of other ellipticals, a fuzzy blob, old stars, no spiral structure, no active star formation. Nothing about its visible appearance suggests it's special. If you pointed an optical telescope at it, you would catalogue it, note its distance, maybe measure its mass, and move on. But in radio wavelengths it transforms. The galaxy sits at the center of 2 enormous lobes of radio-emitting plasma, extending outward in opposite directions like wings. The lobes are faint. The radio emission is spread out over such a vast area that the surface brightness is extremely low. Early radio surveys missed them entirely because the instruments were not sensitive enough to detect such diffuse structures. LOFAR, with its ability to observe at low frequencies and integrate signals from dozens of dishes spread across Europe, finally had the sensitivity needed to see what was there. When the team measured the full extent of the lobes, they got a number that initially seemed absurd: 5 megaparsecs. 1 megaparsec is about 3.26 million light-years. 5 megaparsecs is 16.3 million light-years. That's the distance from the tip of one lobe, through the core of the host galaxy, to the tip of the opposite lobe. The single largest structure of galactic origin ever detected. There's a very important distinction that needs to be made here because the headlines that followed the discovery were not always careful about it. Alcyoneus is not the largest galaxy in terms of stellar extent. IC 1101 still holds that title. IC 1101's visible core contains 100 trillion stars spread across 500,000 light-years, with a halo that may extend to 4 million light-years depending on how you measure it. The stars, the actual glowing balls of fusing hydrogen that we think of when we picture a galaxy, cover a much larger volume in IC 1101 than they do in Alcyoneus. Alcyoneus's host galaxy is big, but not exceptionally so. It's a large elliptical, maybe a few 100,000 light-years across in its stellar body. Mass estimates vary depending on the source and the method used, but most converge on something in the range of a few 100 billion solar masses. Some sources report higher numbers, up to 1 trillion or more, likely including dark matter. Either way, it's a massive galaxy by any reasonable standard, but it's not in the same weight class as IC 1101. It doesn't have 100 trillion stars. It doesn't have a halo stretching millions of light-years filled with the corpses of consumed galaxies. In terms of the traditional metrics we use to measure galaxies, Alcyoneus is large but not record-breaking. What makes Alcyoneus special is not the galaxy. It's what the galaxy did. The 16 million light-year measurement is not counting stars. It's counting the radio lobes. The vast clouds of plasma launched by the black hole at the galaxy's center, inflated by jets that have been running for tens of millions of years, carving through the intergalactic medium and leaving behind a structure so large that it redefines what we mean when we talk about the influence of a galaxy. So the question of whether Alcyoneus is the largest galaxy ever found depends entirely on how you define the word galaxy. If you define it as the region where stars are gravitationally bound to a common center, then IC 1101 is still the champion. If you define it as the total extent of structures created by the galaxy's central black hole, then Alcyoneus wins by a factor of 4. Both definitions are valid. Both measure something real. And the fact that they give different answers tells you that the concept of a galaxy is more complicated than a simple boundary drawn around a cluster of stars. Let's talk about the lobes, because that's where the scale becomes genuinely unsettling. The lobes are not solid. They're not even dense by any normal standard. They're clouds of plasma, ionized particles, mostly electrons and protons, mixed with magnetic fields and high-energy radiation. The density is so low that if you could somehow stand inside one of the lobes, you would experience it as a perfect vacuum. There's less than 1 particle per cubic centimeter in most of the volume. For comparison, the air you're breathing right now contains about 10 to the 19th particles per cubic centimeter. The lobe is emptier than the best laboratory vacuums humans have ever created on Earth, but the volume is so enormous that even at that absurdly low density, the total mass adds up. Each lobe contains the equivalent of billions of solar masses worth of material, not in the form of stars or planets or anything you could touch, just plasma. Hot ionized gas glowing faintly in radio wavelengths, held together by magnetic fields that thread through the structure like scaffolding. The lobes are roughly symmetrical, extending in opposite directions from the host galaxy. That symmetry tells you something important. It means the jets that inflated them were stable over the entire time the lobes were forming, tens of millions of years at minimum. Possibly longer. If the jets had wobbled or precessed, if the direction of the outflow had changed even slightly, the lobes would be lopsided or curved. They're not. They're straight, which means the black hole's spin axis stayed fixed, the accretion disk stayed aligned, and the jets kept firing in the same direction without interruption for longer than the entire history of complex life on Earth. That's hard to do. Black holes don't sit in isolation. They're embedded in galaxies that are themselves embedded in clusters. Other galaxies pass nearby. Gravitational interactions tug on the black hole's host galaxy. Gas falls in from different directions at different times. All of that should cause the jets to shift direction. The fact that Alcyoneus's jets didn't shift tells you the environment was unusually stable. No major mergers, no close encounters with other massive galaxies, just a steady, uninterrupted flow of gas into the black hole, feeding the jets, inflating the lobes, for long enough to carve out a structure 16 million light-years across. The black hole itself is not particularly exceptional. Estimates place its mass at about 400 million times the mass of the Sun. That's large. That's definitely in the supermassive category. But it's not a record breaker. The black hole at the center of IC 1101 is 100 times more massive. The black hole at the center of the quasar Tonnensintler 618 is more than 150 times more massive. 400 million solar masses is well within the range of what you'd expect to find at the center of a large elliptical galaxy. Nothing about the black hole's mass explains why Alcyoneus is so large. That was the first surprise. The team expected to find a monster black hole at the center, something weighing tens of billions of solar masses, something that could pump out jets with so much power that inflating 16 million light-year lobes would be a natural consequence. Instead, they found a black hole that's big but not extraordinary, which means the size of Alcyoneus is not a result of extreme black hole mass. It's a result of something else. The leading explanation is the environment. Alcyoneus sits in a region of space where the intergalactic medium is unusually sparse, low density. The gas between galaxies in that part of the universe is thinner than average, and when jets plow through thin gas, they travel farther before they lose energy and stall out. Think of it like the difference between running through air and running through water. In air you can keep going for miles, in water you slow down almost immediately. The jets from Alcyoneus are running through air. They have room to expand. And because the environment is so empty, the lobes can grow to enormous sizes without being confined or crushed by the pressure of the surrounding medium. This is a critical insight because it suggests that the largest radio galaxies are not necessarily powered by the most massive black holes. They're powered by black holes that happen to be in the right place, low-density environments where the jets can propagate freely over millions of light-years without hitting resistance. That changes the picture. It means the upper limit on radio galaxy size is not set by the black hole's mass or the power of the jets. It's set by the environment. And in the emptiest regions of the universe, that limit might be much higher than anyone expected. The Discovery team ran simulations to test this idea. They modeled jets propagating through different densities of intergalactic gas and asked how large the lobes would grow over a given amount of time. In high-density environments, like the cores of massive galaxy clusters, the jets stall out quickly. The lobes reach a few 100,000 light-years and stop growing. In low-density environments, like the outskirts of clusters or the voids between clusters, the jets keep going. The lobes grow to a few million light-years, and in the very lowest density environments, the lobes can reach 10 million light-years or more. Alcyoneus fits the pattern. It sits in a relatively sparse region, not a complete void, but not a dense cluster core either. And the jets have had enough time to inflate the lobes to their current size without running into anything that would stop them. The implication is unsettling. If Alcyoneus can exist in a moderately low-density environment, what happens in the absolute lowest density regions? Are there radio galaxies out there with lobes stretching 20 million light-years? 30? Is there an upper limit at all? Or do the lobes just keep growing until the jets run out of fuel? We don't know. The sample size is too small. Alcyoneus was only discovered 2 years ago. LOFAR has surveyed a tiny fraction of the sky. There are probably dozens, maybe hundreds, of similar structures out there waiting to be found. Every time someone points a sensitive radio telescope at a new patch of sky, new giants show up. And every time, the definition of what counts as large gets pushed a little further. Let's talk about what it would look like to stand near Alcyoneus, because that's where the scale stops being an abstract number and starts being something you can almost picture. Imagine you're somehow transported to a location near the host galaxy, a few 100,000 light-years from the core, close enough to see the galaxy as a bright smudge in one direction. You look in the opposite direction and you see nothing. No stars, no galaxies. Just empty space stretching in every direction. You're inside one of the lobes, but you can't see it. The plasma is too diffuse. The radio emission is too faint. To your eyes, it looks like a perfect void, but if you had a radio telescope, you'd see the structure, a faint glow filling half the sky, brightest near the core of the galaxy and fading gradually as you look outward. The glow extends in a narrow cone, tracing the path of the jet that inflated the lobe. And somewhere far in the distance, millions of light-years away, the glow reaches its maximum extent and stops. That's the edge of the lobe, the place where the jet material has finally lost enough energy that it can no longer push against the intergalactic medium. The place where the structure ends. You're standing inside the largest known structure created by a single galaxy, a cloud of plasma 16 million light-years across, inflated by a black hole that weighs 400 million suns, sitting at the center of a galaxy 3.5 billion light-years from Earth. And you can't see any of it with your eyes. You're surrounded by one of the most energetically extreme phenomena in the universe, and your senses tell you there's nothing there. That's the eerie part. The scale is so large, and the density is so low that the structure is effectively invisible unless you're looking at the right wavelength. Alcyoneus is not bright. It's not loud. It's not doing anything that would register as dramatic if you were standing next to it. It's just there, quietly, patiently, stretching across a volume of space so large that it makes our galaxy look like a grain of sand on a beach. There's another reason Alcyoneus matters beyond the raw scale. The lobes are fossils. They're records of the black hole's activity over tens of millions of years. By studying the spectrum of the radio emission, the shape of the lobes, the way the plasma is distributed, astronomers can reconstruct what the jets were doing at different points in the past. They can see when the jets were strong and when they were weak. They can see when the black hole was feeding heavily and when it slowed down. The lobes are not snapshots, they're movies, slow-motion recordings of a black hole's life, stretched across millions of light-years. The team that discovered Alcyoneus used the radio data to estimate how long the jets have been running. The answer is somewhere between a few tens of millions of years and 100 million years. That's a long time. Long enough for continents to drift across Earth's surface, long enough for entire species to evolve and go extinct, long enough for stars to form, live their lives and die. And throughout all of that, the jets kept firing, the black hole kept feeding, the lobes kept growing. But the jets are not running now, or if they are, they're much weaker than they used to be. The lobes are old. The plasma has cooled. The radio emission is faint. If the jets were still active at full strength, the lobes would be brighter. The edges would be sharper. There would be visible hotspots where the jets are currently slamming into the intergalactic medium. Instead, the lobes are diffuse and fading, which means the black hole has stopped feeding, or at least slowed down dramatically. The jets have shut off. The structure we're seeing is the remnant of an event that ended millions of years ago. That raises a question: how many other structures like this are out there, fading into the background, invisible to all but the most sensitive instruments? How many black holes have inflated giant lobes, exhausted their fuel supply, and left behind faint ghosts that we haven't detected yet? The universe could be full of these things. Enormous structures scattered across the sky, marking the locations of black holes that went quiet long before humans existed. We're only just starting to develop the instruments sensitive enough to see them. Alcyoneus also changes the conversation about what a galaxy can do. For most of history, we've thought of galaxies as self-contained systems, stars orbiting a common center, gas clouds collapsing to form new stars, black holes sitting quietly at the core. The galaxy's influence extends as far as its gravitational reach, maybe a few times the radius of its stellar body. Beyond that, it's just empty space. The galaxy doesn't matter anymore. Alcyoneus says otherwise. A galaxy's influence can extend far beyond its stars. The black hole at the center can launch jets that propagate for millions of light years, heating the intergalactic medium, disturbing the gas, preventing it from cooling and forming new galaxies. The energy injected by those jets doesn't stay local, it spreads, it ripples outward. And over tens of millions of years, a single galaxy sitting in the right location can shape the temperature and density of the space around it over a volume thousands of times larger than the galaxy itself. That has implications for how structure forms in the universe. The standard picture is that galaxies grow by accreting gas from the intergalactic medium. The gas cools, falls inward, forms stars. Repeat. But if the intergalactic medium is being heated by jets from nearby radio galaxies, the gas can't cool. It stays hot, it stays diffuse, and star formation gets suppressed. Not just in the galaxy producing the jets, but in neighboring galaxies that happen to sit in the heated region. Alcyoneus is doing that right now. Its lobes are heating the intergalactic medium over a volume 16 million light-years across. Any galaxy sitting in that volume is swimming in hot plasma. The gas around those galaxies is hotter than it would be otherwise. The cooling time is longer, the star formation rate is lower, and the reason is a single black hole that shut off millions of years ago but left behind a structure so large that its influence is still being felt today. This is feedback on a cosmic scale. Not just local feedback where the black hole heats the gas in its own galaxy. Global feedback where the black hole heats the gas in an entire region of the universe. And the largest radio galaxies, objects like Alcyoneus, are the most extreme examples of this process. They're not just galaxies, they're environmental regulators, thermostats. They control the temperature of the space around them, and in doing so, they control whether new stars can form in that space. That's why astronomers care about finding the largest radio galaxies. It's not just about setting records, it's about understanding how energy flows through the universe, how black holes influence their surroundings, how the structures we see today were shaped by events that happened tens or hundreds of millions of years ago. Every giant radio galaxy is a piece of that puzzle, and Alcyoneus, with its 16 million light-year lobes, is the biggest piece we've found so far, except it's not. Because while Alcyoneus held the record for the largest structure of galactic origin for a brief moment, it didn't hold it for long. Within 2 years of its discovery, LOFAR surveys turned up something even larger. Another radio galaxy with lobes so vast that they make Alcyoneus look modest by comparison. A structure so large that when the measurement was first published, it forced astronomers to reconsider whether there's any meaningful upper limit to how large these objects can grow. Its name is Porphyrion, and it is where the concept of a galaxy stops making sense entirely. Alcyoneus held the record for 2 years. 2 years during which astronomers looked at those 16 million light-year lobes and thought, surely that's the limit. Surely we've found the edge of what's possible. Surely there can't be anything larger sitting out there waiting to be discovered. Nature has a habit of ignoring what we think is possible. And in 2024, a team led by Martin Oey at the California Institute of Technology was combing through data from the low-frequency array when they found something that made Alcyoneus look like a practice run. They found Porphyrion, and when they measured it, the number that came back was so absurd that the team spent months double-checking the analysis before they were willing to publish. 23 million light-years, end to end, lobe to lobe, a single structure, powered by a single supermassive black hole, stretching across a distance so vast that it forces a fundamental rethinking of what a galaxy can do to the space around it. Porphyrion is not just larger than Alcyoneus. It is not just the new record holder. It is the kind of discovery that breaks the conversation. Because when you start talking about structures 23 million light-years across, you are no longer talking about galaxies in any traditional sense. You are talking about objects that shape the universe at the scale of the cosmic web itself. Objects whose influence extends across distances so large that they can affect the formation and evolution of other galaxies millions of light-years away. Objects that make IC 1101's 4 million light-year halo look like a suburb, and Alcyoneus's 16 million light-year lobes look like a warm-up act. The name comes from Greek mythology, the same tradition that gave us Alcyoneus. Porphyrion was one of the Gigantes, the giants born from the blood of Uranus when he was overthrown by the Titans. During the war between the giants and the Olympian gods, Porphyrion was the largest and most powerful of the giants, strong enough to challenge Zeus himself. The name fits. This is not a large radio galaxy. This is the largest structure of galactic origin ever found. Period. Full stop. Nothing else comes close. The host galaxy sits in the constellation Draco, about 7.5 billion light-years from Earth. The catalog designation is J152932.16 plus 601534.4, which tells you nothing except that it was logged in a survey and assigned a number based on its coordinates. In optical light it looks unremarkable, a faint smudge, too distant to resolve individual stars, too faint to stand out against the thousands of other distant galaxies scattered across the same patch of sky. Nothing about its visible appearance suggests it's special, but the team wasn't looking at optical light. They were looking at LOFAR data, low-frequency radio observations covering a large swath of the northern sky. And when they processed the data for that particular region, two enormous lobes appeared on either side of the host galaxy. Lobes so large that at first the team thought they were looking at two separate radio sources that happened to be aligned by chance. They were not. Follow-up observations confirmed that both lobes were part of the same system. Jets launched from a single black hole, propagating in opposite directions, inflating two symmetric clouds of plasma, and when they measured the distance from the tip of one lobe to the tip of the other, the number came back at about 7 megaparsecs. 1 megaparsec is 3.26 million light-years. 7 megaparsecs is 22.8 million light-years. Call it 23 million to keep the math simple. That's the span, the full extent of the structure. And it is the largest measurement of any galactic structure ever recorded. Porphyrion is twice the size of Alcyoneus. It is nearly 6 times the size of IC 1101's halo. It is 140 times the width of the Milky Way. 140. If you lined up 140 Milky Way galaxies edge to edge, you would span the distance from one end of Porphyrion to the other. That is not a metaphor. That is the actual ratio. A single structure created by a single object, extending across a volume of space large enough to fit more than 100 of our galaxies in a row. Let's try to put that in a context that feels real, because I don't think the number has landed yet. The Milky Way is about 100,000 light-years across. Light leaving one edge of our galaxy takes 100,000 years to reach the other edge. That is already an incomprehensibly large distance by human standards. Now multiply that by 140. Porphyrion's jets span 14 million times the width of our solar system. If you placed Porphyrion where the Milky Way sits, one of its lobes would stretch past Andromeda, past the entire local group, across the space between galaxy groups, and into a region so far from anything familiar that we don't have common names for the structures out there. The other lobe would stretch in the opposite direction, past every dwarf galaxy in our neighborhood, past the edge of our local supercluster, and into the voids between superclusters. You would not be looking at a structure that dominates a galaxy group. You would be looking at a structure that dominates multiple galaxy groups. A structure so large that it reaches across the boundaries between the largest gravitationally bound systems in the universe. Here is the part that should bother you. Porphyrion is not in our neighborhood. It is 7.5 billion light-years away. The light we are detecting left the host galaxy when the universe was 6.3 billion years old, less than half its current age. The solar system did not exist. The sun had not formed. The Milky Way was still in the process of assembling itself through mergers with smaller galaxies, and at that moment in cosmic history, a black hole sitting at the center of a distant elliptical galaxy turned on, started feeding, launched jets, and carved out a structure 23 million light-years across. That structure existed billions of years before Earth was born. It is still there. The jets are not running anymore, or if they are much weaker than they used to be. The lobes we see today are the remnants of an event that ended long ago, but the plasma is still glowing. The magnetic fields are still threaded through the structure, and the radio emission is still strong enough that we can detect it from 7.5 billion light-years away. The Discovery team used LOFAR to detect the lobes and then followed up with spectroscopy from the Keck 1 telescope in Hawaii to confirm the distance. Spectroscopy splits incoming light into its component wavelengths, allowing astronomers to measure the redshift of the host galaxy. Redshift is the stretching of light caused by the expansion of the universe. The more stretched the light, the farther away the object, and the longer the light has been traveling. Porphyrion's redshift came in at 0.896, plus or minus 0.001. That number places the galaxy firmly in the early universe, long before most of the galaxies we see in our local neighborhood had settled into their current forms. And at that distance, the angular size of the lobes on the sky translates to a physical size of 23 million light-years. There is no ambiguity in the measurement. The team checked the calibration. They checked the distance. They checked whether the two lobes might be separate objects that just happened to line up. They ruled out every alternative explanation. Porphyrion is real. It is as large as the data says it is, and it is sitting in the record books as the largest structure of galactic origin ever found. The black hole at the center is not particularly extreme. Estimates place its mass somewhere in the range of a few 100 million to a billion solar masses. Large, yes, supermassive by any definition, but not a record breaker. Not the kind of black hole that would make you expect jets spanning 23 million light-years. The black hole at the center of IC 1101 is 40 to 100 times more massive. The black hole at the center of the quasar TUN 618 is more than 60 times more massive. Porphyrion's black hole is, by supermassive black hole standards, relatively ordinary, and yet it produced the largest jets ever observed. That tells you the same thing Alcyoneus told you. The size of a radio galaxy is not primarily determined by the mass of the black hole. It is determined by the environment, by how long the jets can propagate before they run out of space or energy, by how thin the intergalactic medium is in the region where the galaxy sits, and by how long the jets stay active without being disrupted or shut down by external forces. Porphyrion's jets have been propagating for roughly 2 billion years. 2 billion. That is not a typo. The team estimated the age of the jets by analyzing the spectrum of the radio emission and modeling how long it would take for plasma to travel from the core to the edges of the lobes. The answer came back at about 2 billion years. That is longer than it took for life on Earth to evolve from single-celled organisms to complex multicellular life. That is longer than the time it takes for continents to drift across the planet's surface multiple times. That is longer than the lifespan of most stars in the universe. And throughout that entire span of time, the jets kept firing, the black hole kept feeding, the lobes kept growing. 2 billion years is an absurdly long time for a black hole to stay active. Most active galactic nuclei turn on and off on much shorter timescales, a few million years, maybe a few tens of millions. The black hole feeds for a while, exhausts the available gas, and shuts down. The jets stop, the lobes fade, and the galaxy goes quiet until the next merger or interaction funnels fresh gas into the core. Porphyrion did not shut down, it stayed on for 2 billion years. That implies an unusually steady supply of fuel, an unusually stable configuration where gas kept falling into the black hole at a rate high enough to sustain the jets, but not so high that it triggered feedback mechanisms that would shut the whole system down. And it implies that the host galaxy avoided major disruptions during that time. No large mergers, no close encounters with other massive galaxies, no gravitational kicks that would have reoriented the black hole's spin axis and changed the direction of the jets. For 2 billion years, everything stayed aligned, everything stayed stable, and the jets kept carving through the intergalactic medium. Here is where the scale gets uncomfortable. The lobes are not contained within a galaxy cluster. They are not confined to a single supercluster. They extend across the cosmic web itself. The cosmic web is the large-scale structure of the universe. If you could step back and look at the distribution of galaxies across the entire observable universe, you would see that they are not randomly scattered. They are arranged in filaments, long, thin threads of galaxies connected by gravity, separated by vast, empty regions called voids. The filaments wrap around the voids like the strands of a spiderweb. Where filaments intersect, you get clusters, dense regions where hundreds or thousands of galaxies pile up. In between the filaments, you get voids, regions hundreds of millions of light-years across where almost no galaxies exist. The cosmic web is the skeleton of the universe. It is the framework on which everything else is built. And Porphyrion's jets span a significant fraction of that framework. The lobes extend across a distance comparable to the radius of a large cosmic void. 23 million light-years is not the full width of a void. Voids can be 100 million light-years across or more, but it is a substantial fraction. Enough that if Porphyrion sat near the edge of a void, its jets could extend across a significant portion of the empty space, reaching from one filament toward another. That is the scale we are talking about. A single galaxy sitting somewhere along a filament of the cosmic web, launching jets that propagate across the void, heating and disturbing the intergalactic medium over distances so large that the structure becomes part of the cosmic web's architecture. Porphyrion is not just a galaxy with jets, it is a bridge. A connection between regions of space that would otherwise be separated by millions of light-years of empty void. The jets are channels. They carry energy from the black hole at the galaxy's core outward into the intergalactic medium, depositing that energy across a volume large enough to affect the temperature and density of the space between galaxies on truly cosmic scales. This has implications, big ones. One of the outstanding questions in cosmology is how energy gets distributed through the universe. Stars produce energy, supernovae produce energy, black holes produce energy, but how does that energy spread? How does it move from the dense regions where galaxies sit out into the voids where almost nothing exists? For a long time, the assumption was that energy stays local. It heats the gas in and around the galaxy that produced it, but it doesn't travel far. The voids stay cold and empty because there is nothing out there to heat them. Porphyrion says otherwise. The jets are carrying energy across distances of tens of millions of light years. They are heating the intergalactic medium far from the host galaxy. They are disturbing gas that would otherwise be undisturbed. And they are doing it on timescales of billions of years. That means the energy budget of the universe is more complicated than the simple models predicted. Energy is not staying local, it is spreading. And the agents of that spreading are the jets from supermassive black holes in galaxies like Porphyrion. There is another implication. The jets are not just heating the gas, they are magnetizing it. The plasma in the lobes is threaded with magnetic fields. Those fields are strong enough to confine the plasma and keep the lobes from dispersing immediately. And as the lobes expand, they push those magnetic fields outward into the intergalactic medium. Over time, the entire region around Porphyrion becomes magnetized. The fields are weak by laboratory standards, but they are there, and they can affect how gas moves, how it cools, and how it eventually collapses to form new galaxies. Magnetized gas behaves differently than unmagnetized gas. It is harder to compress, it resists collapse, and it can suppress star formation over large regions. If enough radio galaxies are pumping magnetic fields into the cosmic web, the cumulative effect could be significant. It could change the rate at which new galaxies form in the late universe. It could explain why star formation has been declining over the last few billion years. It could be part of the feedback mechanism that regulates how much of the universe's gas gets turned into stars and how much stays in the intergalactic medium forever. That is speculative. The data is not there yet. But the fact that we are even having this conversation, the fact that a single galaxy's jets can extend far enough to matter on cosmic scales, is a profound shift in how we think about the role of black holes in shaping the universe. Let's go back to the environment, because that is the key to understanding why Porphyrion exists at all. The jets are traveling through the intergalactic medium, the thin gas that fills the space between galaxies. In dense regions like the cores of galaxy clusters, that gas is hot and dense. Hot gas exerts pressure. When jets plow through hot, dense gas, they slow down quickly. They deposit their energy into the surrounding medium, inflating lobes that reach a few 100,000 light-years and then stall. The gas pressure is too high. The jets can't push any further. The lobes stop growing. In low-density regions, the gas is cooler and much thinner. There is less pressure pushing back against the jets. The jets can propagate much farther before they lose energy. The lobes grow larger. And in the lowest density regions, the voids and the edges of voids, the gas is so thin that the jets can travel for millions of light-years before they encounter enough resistance to stop. Porphyrion sits in one of those low-density regions, not a complete void. If it were sitting in the absolute center of a void, there would be no gas to feed the black hole in the first place, but not a dense cluster core either. Somewhere in between, a region where the intergalactic medium is thin enough that the jets can propagate freely, but not so thin that the galaxy is starved of fuel. That balance is critical. Too much gas and the jets stall out. Too little gas and the black hole shuts down. Porphyrion found the sweet spot, and it stayed in that sweet spot for 2 billion years. The fact that such regions exist and that they can sustain jet propagation over these distances changes the picture of how the universe is structured. For a long time, astronomers thought of the cosmic web as a static framework, filaments and voids, dense and empty. The dense regions are where the action happens. The empty regions are where nothing happens. Porphyrion is doing something in the empty regions. It is threading energy through the voids. It is connecting filaments. It is acting as a conduit, moving energy from the dense regions where galaxies live out into the vast empty spaces where almost nothing exists. And it is not unique. The Discovery team found other large radio galaxies in the same survey, not as large as Porphyrion, not 23 million light-years, but large enough to matter. Structures with lobes extending 10 or 15 million light-years, dozens of them scattered across the survey area, which suggests that Porphyrion is not a freak. It is the extreme end of a distribution. There are probably hundreds or thousands of radio galaxies out there with jets spanning tens of millions of light-years, threading through the cosmic web, heating and magnetizing the intergalactic medium, shaping the environment in ways we are only just beginning to understand, and we have only surveyed a tiny fraction of the sky. LOFAR has covered maybe 10 or 20% of the northern hemisphere at the sensitivity needed to detect these faint diffuse structures. The southern hemisphere is almost completely unmapped at these wavelengths. There are probably radio galaxies in the southern sky just as large as Porphyrion, maybe larger, that we have not found yet because we have not looked. Every time someone points a sensitive low-frequency radio telescope at a new patch of sky, new giants show up. The sample size keeps growing, and every new discovery pushes the definition of what counts as large a little further. Here is the uncomfortable question. Is there a limit? Is there a maximum size a radio galaxy can reach? Or do the jets just keep growing until the black hole runs out of fuel? The answer depends on the environment. In a dense region, there is a hard limit. The gas pressure stops the jets. In a low-density region, the limit is softer. The jets can keep going as long as the black hole keeps feeding and the intergalactic medium stays thin. If the black hole feeds for a few billion years and the environment stays favorable, the jets could reach 50 million light-years, 100 million. Maybe more. We do not know. The physics at those scales get speculative. The jets would be propagating through regions where the gas density is so low that the concept of pressure almost breaks down. The lobes would be so diffuse that detecting them would require instruments even more sensitive than LOFAR. And the timescales would be so long that only a tiny fraction of galaxies would ever reach those sizes, because most black holes do not stay active for billions of years. But the fact that Porphyrion exists, the fact that it reached 23 million light-years, tells you that the upper limit is higher than anyone expected, much higher. And the only way to find that limit is to keep looking, keep surveying, keep building more sensitive telescopes, keep pushing the detection threshold lower until we either find something larger or we exhaust the available parameter space and conclude that Porphyrion is as large as nature allows. The other thing Porphyrion tells you is that the universe was doing this early. 7.5 billion light-years away means 7.5 billion years in the past. The universe was 6.3 billion years old when Porphyrion's jets started propagating. That is less than half the current age of the universe. It is early, and it means that supermassive black holes capable of launching jets this powerful and sustaining them for this long existed much earlier in cosmic history than most models predicted. That is the same problem we saw with IC 1101. That is the same problem we saw with the earliest galaxies detected by the James Webb Space Telescope. Things that should take billions of years to build were built much faster. Black holes that should take billions of years to grow were already in place when the universe was still young. And structures that should not exist at early times were already shaping the environment on cosmic scales. Porphyrion is another data point in that growing list of things that do not fit comfortably into the standard models. It is not breaking physics. The jets obey the laws of relativity. The plasma obeys the laws of magnetohydrodynamics. The black hole obeys the laws of general relativity. But the combination, the fact that all of those processes conspired to produce a structure 23 million light-years across in the early universe, is not something the models predicted. It is something the models now have to explain, and that is how science works. You build a model that fits the data, then you find new data that does not fit, and you refine the model, you add complexity, you adjust the parameters, you test new hypotheses, and eventually you build a better model that fits both the old data and the new data. Porphyrion is the new data. It is the structure that forces a refinement. And the fact that it exists at all is a reminder that the universe is larger, stranger, and more energetically extreme than the models built on observations of nearby, well-behaved galaxies would ever have predicted. There is one more thing worth saying about Porphyrion before we move on. The structure is invisible to the human eye. You cannot see it in optical light. You cannot see it in infrared. You cannot see it in X-rays. The only way to detect it is with a radio telescope operating at low frequencies, which means that for most of human history, for the entire span of time that people have looked up at the night sky and wondered what was out there, Porphyrion was invisible. It was there. It existed. It was threading energy across the cosmic web, shaping the intergalactic medium, influencing the formation of galaxies millions of light-years away. But no one knew, no one could know, because the tools to detect it did not exist. It took until 2024, until LOFAR had surveyed enough sky at high enough sensitivity for someone to finally see it. And now that we have seen it, we have to reckon with what it means. A structure 23 million light-years across, created by a single black hole, existing in the early universe, shaping the environment on scales so large that it affects the cosmic web itself. That is not a galaxy anymore. That is something else, a new category of object that does not fit neatly into any of the definitions we have been using. It is a bridge between the world of galaxies and the world of cosmic structure, a reminder that the boundaries we draw, the categories we create, are tools for organizing our understanding, not fundamental features of nature. And when nature produces something like Porphyrion, something that shatters the categories and forces a rethinking of the boundaries, the only honest response is to admit that the universe is larger and stranger than we thought. Which brings us to the final question, the one that has been sitting underneath this entire discussion. If the largest known structure of galactic origin is 23 million light-years across, and if that structure is part of a distribution that includes dozens or hundreds of similar objects, and if the upper limit on how large these structures can grow is still unknown, then what does the word galaxy even mean anymore? What are we measuring when we talk about the size of a galaxy? Where do we draw the line between the galaxy and the space around it? And at what point does the scale become so large that the concept of a single object stops making sense entirely? Those are not easy questions, and the answers, if there are answers, are going to depend on how we choose to define the boundaries. But the fact that we are even asking them, the fact that objects like IC1101 and Alcyoneus and Porphyrion have pushed the scale so far that the definitions no longer hold, is a sign that we are reaching the edge of something, not the edge of the universe, the edge of comprehension, the place where the numbers stop meaning what they used to mean and the scale stops being something the human brain can hold. That is where we are going next, to the place where scale shatters and meaning dissolves, to the question of what happens when you try to think about things so large that thinking itself becomes inadequate. We've spent the better part of this journey talking about galaxies as though they're things we can understand, objects with boundaries, structures with beginnings and ends, things you could, in principle, measure completely if you had the right instruments and enough time. That assumption has been quietly eroding since we started talking about IC 1101's halo, and by the time we got to Porphyrion, it collapsed entirely. But we've been moving too fast to stop and acknowledge what just happened, so let's do that now. Let's talk about what it means when the scale gets so large that comprehension itself starts to break down. IC 1101 was the warm-up. 550,000 light-years across in its visible stellar body, 100 trillion stars packed into a region that stretches 5.5 times wider than the Milky Way, a halo extending another few million light-years beyond that, depending on how generously you measure. 4 million, maybe 6. The numbers are uncomfortable, but they're still numbers you can write down, visualize with the right mental gymnastics, and place into some kind of framework. IC 1101 is a galaxy, a very large galaxy. The largest collection of stars we've ever found, bound together in a single gravitational system. That much is clear. Then came Alcyoneus, 16 million light-years from one end to the other. Not stars this time. Radio lobes, plasma inflated by jets, launched from a black hole at the center of an otherwise unremarkable elliptical galaxy. The lobes stretch 4 times farther than IC 1101's halo. They extend across a volume of space large enough to contain the entire local group with room to spare, and they're part of a structure created by a single galaxy, powered by a single black hole. The result of jets that ran for tens of millions of years without stopping, carving through the intergalactic medium, leaving behind a scar so large it redefined what a galaxy could do to the space around it. And then Porphyrion, 23 million light-years. Jets that propagated for 2 billion years, threading energy across the cosmic web, heating and magnetizing the intergalactic medium over distances so vast that the structure becomes part of the framework of the universe itself. A single object, created by a single black hole, extending across a region large enough that calling it a galaxy feels inadequate. It's something else. A bridge between galaxy and cosmic structure, a reminder that the categories we've built to organize the universe are tools, not truths, and when nature produces something that doesn't fit the categories have to change. So here's the question we've been avoiding. What are we actually measuring when we talk about the size of these things? Where does the galaxy stop and the space around it begin? And at what point does the scale become so large that the word galaxy stops meaning anything useful? There's no clean answer. The definitions are messy. They always have been. For most of history, a galaxy was simple. A collection of stars. You could see them through a telescope. You could count them, or at least estimate how many there were. You could measure how far the starlight extended and draw a boundary. Inside the boundary, galaxy, outside, space. Easy. Then we found the halos, diffuse clouds of old stars, globular clusters, tidal streams from galaxies that had been torn apart and absorbed, material that was clearly part of the galaxy but didn't fit the simple picture of a bright disk or ellipsoid. The halos extended much farther than the visible body, so the definition shifted. A galaxy became not just the bright part, but the region where stars were still gravitationally bound to the center. That worked for a while. Then we found the dark matter halos, invisible structures extending even farther, detectable only through their gravitational effects on the stars and gas. The dark matter halo of the Milky Way might reach out to a few 100,000 light-years, maybe more. It blends gradually into the space between galaxies. There's no sharp edge, just a slow fading of density until you can't tell where the galaxy ends and the intergalactic medium begins. So the definition shifted again. A galaxy became the region dominated by its own dark matter halo. That worked too, sort of, as long as you didn't look too closely at the boundaries. And then we found the radio galaxies. Jets extending millions of light years, lobes inflated by plasma launched from the central black hole, structures that have nothing to do with stars or dark matter or gravitational binding. They're products of the black hole's activity. Energy carried outward by relativistic jets and deposited into the space between galaxies. Are those lobes part of the galaxy? They're created by the galaxy. They're powered by the galaxy. But they're not gravitationally bound to it. They're not made of stars. They're not even particularly dense. They're just there, faint clouds of plasma glowing in radio wavelengths, marking the extent of the galaxy's influence. So what do we call them? Are they part of the galaxy or not? The answer depends on what you're trying to measure. If you're measuring the galaxy's gravitational reach, you ignore the lobes. If you're measuring the galaxy's energetic influence, you include them. If you're measuring the total extent of structures created by the galaxy, the lobes are the most important part. 3 different definitions, 3 different answers, and no way to say which one is correct because they're all measuring something real. That ambiguity is not a bug, it's a feature. It's the universe telling us that the categories we've built are too rigid, that galaxies are not discrete objects with well-defined boundaries. They're processes, ongoing events, regions where matter and energy are doing interesting things, and the extent of those regions depends on what you're looking for. IC 1101 is the largest galaxy if you define a galaxy by its stars. Alcyoneus is the largest if you include radio lobes but stop at 16 million light-years. Porphyrion is the largest if you push the definition all the way to 23 million light-years. And there might be something even larger out there that we haven't found yet because we haven't surveyed the right part of the sky or built the right instrument. The record keeps changing. Not because the universe is changing, but because our ability to see it is improving. Every new telescope, every deeper survey reveals structures that were always there but invisible to the instruments we had before. Here's what that means in practical terms. The largest galaxy is not a fixed thing, it's a moving target. And the reason it's moving is not because galaxies are growing faster than we thought, though some of them are still growing. It's because the definition of what counts as a galaxy is expanding to include structures we didn't know existed. Radio lobes, tidal streams, diffuse halos, magnetic fields threading through the intergalactic medium. All of these are products of galactic activity. All of them extend far beyond the region where stars live. And all of them, depending on how you choose to define the word, could be considered part of the galaxy. The philosophical weight of that is heavier than it looks. For most of human history, we thought the universe was small. The Earth was the center. The stars were lights on a dome overhead. Then we realized the stars were suns. Then we realized those suns were grouped into galaxies. Then we realized the galaxies were scattered across billions of light-years of expanding space. Every step expanded the scale. Every step forced us to reckon with the fact that the universe was larger than we'd thought. And every time we adjusted, we built new models, we redrew the maps, we kept going. But there's a limit to how far that process can go before the scale stops being something you can intuitively grasp and starts being something you can only describe mathematically. 100 light-years is large, but you can picture it, a journey that takes 100 years at the speed of light, a sphere containing a few thousand stars. 1,000,000 light-years is harder, but still manageable. It's 1,000 times larger, the distance to Andromeda, a region that contains a few large galaxies and a bunch of smaller ones. You can't see it all at once, but you can build a mental image. 10 million light-years. That's where it starts to slip. You can say the number, you can write it down, But picturing it, holding it in your head as a real distance, becomes almost impossible. The volume is so large that the analogies stop working. Comparisons to familiar objects break down. You're left with the number itself, abstract and cold, sitting in your mind like a stone you can't lift. Now go to 23 million light-years, the span of Porphyrion. That's not a distance anymore. It's a concept. A measurement that exists in equations and data tables but refuses to mean anything when you try to translate it into something you can visualize. You know it's large. You know it's larger than 10 million light-years. But the difference between 10 million and 23 million, the sense of how much larger one is than the other, dissolves. Your brain treats them the same way. Both are too big. Both are beyond the threshold where scale has meaning. And that's the edge we've been talking about, the place where comprehension shatters, not because the universe is doing anything strange, because your brain, the thing that evolved to navigate a world a few miles across, that spent most of its evolutionary history worrying about predators and food and shelter, is being asked to hold a structure 23 million light-years wide. It can't. The machinery isn't there. The intuition that works perfectly well for human-scale distances, the sense of space that tells you how far away the horizon is or how long it will take to walk across a room, fails completely when you scale it up by a factor of 100 billion trillion, so you're left with numbers. Distances measured in light-years or megaparsecs, masses measured in solar masses, timescales measured in billions of years, all of them abstract, all of them requiring translation through mathematics before they mean anything, and even then the meaning is thin. You can calculate how long it would take light to cross Porphyrion's lobes, 23 million years. You can calculate how many Milky Ways would fit across that span, 140. You can list the numbers, recite the facts, explain the structure to someone else. But you can't see it, you can't hold it, you can't feel the scale the way you can feel the scale of a mountain or an ocean or the distance to the moon. That disconnect is humbling. It's a reminder that the universe operates at scales so far removed from human experience that direct understanding is impossible. The best we can do is build models, mathematical descriptions that capture the structure even if they don't capture the sense of it. Tools that let us predict what we'll see when we point a telescope at a distant object, even if we can't picture what that object actually looks like. And here's the uncomfortable part. We're still at the beginning of this process. The largest structures we've found so far, things like Porphyrion and Alcyoneus, are limited by the sensitivity of our instruments. LOFAR can detect faint diffuse radio emission that earlier telescopes missed, but LOFAR has only surveyed a fraction of the sky. The Square Kilometre Array, a next-generation radio telescope currently under construction, will be 10 times more sensitive. When it comes online, it will find structures LOFAR couldn't see, fainter lobes, more distant galaxies, radio jets that have been propagating for so long that the plasma has cooled to the point where only the most sensitive instruments can detect it. We don't know what the Square Kilometre Array will find. That's the point. Every time we build a better telescope, we find things that weren't supposed to be there. Galaxies that are too large, black holes that are too massive, structures that formed too early. The pattern has held for decades. There's no reason to think it will stop, which means the current record holders, IC 1000, 101, and Alcyoneus and Porphyrion, are placeholders, temporary entries in a list that will keep growing as the instruments improve and the surveys get deeper. The upper limit on galaxy size, if there is an upper limit, is still unknown. The physics suggests there should be a limit. Jets can't propagate forever. Eventually, they run out of energy or encounter gas dense enough to stop them. The lobes can't grow indefinitely. Eventually, the plasma cools and fades and the structure becomes undetectable. But where that limit sits, how large a galaxy can get before it hits that ceiling, is a question we can't answer yet. The data isn't there. The models aren't good enough. We're guessing, and the guesses keep getting revised upward. 10 years ago, the largest known radio galaxy was about 15 million light-years across. That seemed like the edge of what was possible. Then Alcyoneus showed up at 16 million. Then Porphyrion at 23 million. Every time we think we've found the limit, something larger appears. The pattern suggests the limit is higher than we thought. Maybe 30 million light-years, maybe 50. Maybe there is no hard limit, just a gradual drop-off in the probability of finding something larger as you push the scale higher. That uncertainty is part of what makes this so disorienting. We're not just talking about galaxies that are larger than expected. We're talking about a regime where the expectations themselves are breaking down, where the models we built to understand galaxy formation and black hole activity and the structure of the intergalactic medium are being tested at scales they were never designed to handle, and the results so far suggest the models are incomplete. Not wrong, incomplete. Missing pieces that only become visible when you look at the most extreme examples. This is how science works. You build a model that explains the data you have. You test it, you refine it, then you find new data that doesn't fit, and you go back and add complexity, new parameters, new processes, new physics. The model gets better, it explains more, but it also gets messier. The clean, simple picture you started with, the one where galaxies were just collections of stars held together by gravity, gets replaced by something more layered. Stars plus dark matter plus gas plus black holes plus jets plus feedback plus magnetic fields plus 100 other things that all interact in ways that are difficult to calculate and impossible to visualize. IC 1101, Alcyoneus and Porphyrion are data points in that process. They're examples of what happens when you take the mechanisms we understand, gravity, accretion, jet formation, and run them for billions of years in environments that are rare but not impossible. They're not breaking the laws of physics, they're showing us what the laws of physics allow when the conditions line up just right. And the fact that they exist at all is a reminder that the universe is capable of producing things we didn't predict, things that push the boundaries of the models and force us to reconsider what we thought we knew. Here's the other thing that makes this humbling. These structures are not special. They're rare, sure. Porphyrion is one of the largest radio galaxies we've found, but it's not unique. The same survey that found Porphyrion found dozens of other large radio galaxies, smaller than Porphyrion but still enormous. 10 million light-years, 15 million, structures that would have been record breakers a decade ago and are now just entries in a catalogue. The universe is full of these things. We're only just starting to detect them because we're only just starting to build instruments sensitive enough to see them. And every time we look deeper, we find more. That means the largest galaxy, whatever that term ends up meaning, is probably not something we've found yet. It's sitting out there somewhere, too faint or too distant or too diffuse for current instruments to detect. And when we finally do find it, when the square-kilometer array or some future telescope picks up a structure 30 or 40 or 50 million light-years across, it will force the same conversation we're having now, the same questions about definitions and boundaries and what it means for something to be part of a galaxy, and the same uncomfortable realization that the scale is larger than we thought, the universe is stranger than we expected, and the limits we assumed were there might not exist. So what's the takeaway? What are we supposed to do with the knowledge that the largest galaxies are so large that comprehending them is impossible? that the structures we're measuring extend across distances that dwarf everything we thought we understood about galactic scale, that the very concept of a galaxy is dissolving into something more complicated, more diffuse, and harder to define. The honest answer is that we keep looking. We build better telescopes. We run deeper surveys. We refine the models. We find new examples. We test the predictions. And slowly, piece by piece, we build a more complete picture of what galaxies are, how they form, and how large they can grow. It's not a fast process. It's not a satisfying one. There's no moment where we solve the puzzle and declare victory. Just a slow accumulation of data, a gradual refinement of understanding, and an ongoing awareness that the universe is under no obligation to fit into the categories we've built for it. But there's something else too, something that matters more than the measurements and the models and the definitions. These discoveries, IC 1101 and Alcyoneus and Porphyrion, are reminders of how little we actually know. We've been studying galaxies for 100 years. We've catalogued millions of them. We've built theories that explain how they form, how they evolve, how they die, and then we point a telescope at a patch of sky and find a structure 23 million light-years across, powered by a black hole we didn't know could stay active for 2 billion years, threading energy across the cosmic web in ways the models didn't predict. And we're forced to admit that the picture we had was incomplete, that the universe is still teaching us, that the edge of knowledge is closer than we thought. That's the real lesson here. Not the specific numbers, though the numbers are staggering, not the specific galaxies, though they're extraordinary. The lesson is humility, the recognition that no matter how much we've learned, no matter how sophisticated the instruments or how detailed the models, the universe keeps producing things that surprise us, things that don't fit, things that force us to go back and reconsider assumptions we didn't even know we were making. And the appropriate response to that is not frustration or confusion, it's curiosity. The same curiosity that drove someone to point a telescope at IC 1101 in the 1800s and wonder what that faint fuzzy blob was. The same curiosity that drove the LO-FAR team to survey the sky at low frequencies and see what they could find. The same curiosity that will drive the next generation of astronomers to build even better instruments and look even deeper and find structures even larger than Porphyrion. Because the edge of comprehension is not a wall, it's not a place where understanding stops and we give up. It's a place where understanding transitions, where direct intuition fails and we have to rely on mathematics and models and abstractions, where the universe stops being something we can hold in our heads and starts being something we describe with equations. It's uncomfortable, it's disorienting, and it's exactly where the most interesting discoveries happen. IC 1101 showed us that galaxies could be larger than we thought. 100 trillion stars, 4 million light-years across if you count the halo. A monument to the slow accumulation of mass over billions of years, sitting at the center of a massive galaxy cluster, quietly devouring everything that drifted too close. It held the title of largest galaxy for decades. It was the example used in textbooks to illustrate the upper end of galaxy size. And then the definition shifted. Alcyoneus showed us that size isn't just about stars, that a galaxy's influence extends far beyond its stellar body, that jets launched by a supermassive black hole can carve through the intergalactic medium for tens of millions of years, inflating lobes 16 million light-years across, heating and magnetizing the space between galaxies, shaping the environment on scales so large that the galaxy itself becomes a tiny dot in the middle of the structure it created. Alcyoneus didn't break the record for stellar extent. It broke the record for total reach, and in doing so it forced a redefinition of what the word galaxy could mean. Porphyrion took that redefinition and stretched it even further, 23 million light-years, jets that ran for 2 billion years, lobes that extend across a significant fraction of the cosmic web, connecting filaments, threading energy through voids, influencing the formation and evolution of galaxies millions of light-years away. Porphyrion is not just a galaxy, it's a bridge, a structure so large that it becomes part of the architecture of the universe itself. And it exists in the early universe, 7.5 billion light-years away, a reminder that the largest structures were already being built when the cosmos was less than half its current age. These are not the last examples we'll find, they're the first, the beginning of a catalogue that will keep growing as the instruments improve and the surveys get deeper. The largest galaxy today is Porphyrion. The largest galaxy tomorrow will be something else. Something fainter, more distant, more diffuse, something that pushes the scale a little higher and the definitions a little further. And every time we find one, we'll have the same conversation, the same questions about boundaries and categories, the same realization that the universe is larger and stranger than we thought. The same uncomfortable awareness that the scale is approaching the edge where comprehension breaks down and we're left with numbers that refuse to mean anything. But we'll keep looking anyway, because that's what curiosity does. It pushes past the edge of comfort, past the point where intuition works, into the space where the only tools left are mathematics and patience and the willingness to sit with the discomfort of not fully understanding. And somewhere in that space, in the gap between what we can measure and what we can comprehend, we'll find the next discovery, the next structure that doesn't fit, the next reminder that the universe is under no obligation to make sense to us. IC 1101, Alcyoneus and Porphyrion are milestones on that journey, markers showing how far we've come and how much further there is to go. They're the largest galaxies we've found so far, not the largest that exist. Not the largest that could exist, just the largest we've managed to detect with the instruments we've built and the definitions we've chosen. And as the instruments get better and the definitions evolve, the milestones will move, the records will change, and the edge of comprehension, the place where scale shatters and meaning dissolves, will keep retreating into the distance, always just out of reach, always beckoning us forward. That's where we are now, standing at the edge, looking out at a universe full of structures so large they defy understanding, and realizing that the only way forward is to keep going, to keep building, to keep looking, to keep asking questions even when the answers are uncomfortable. Because the alternative, stopping at the edge and declaring that this is as far as we can go, is not an option. The universe doesn't care whether we understand it, but we care. And that care, that relentless curiosity, is what will carry us past the edge and into whatever lies beyond. So here's what we're left with. 3 galaxies, 3 different answers to the same question, and the uncomfortable realization that the question itself might be broken. IC 1101 is the largest collection of stars ever found. 100 trillion suns packed into a region 500,000 light-years across, wrapped in a halo that stretches to 4 million light-years depending on how generously you measure. It's a monument, a graveyard, the final resting place for hundreds of smaller galaxies that drifted too close and got torn apart over billions of years. It's what happens when gravity runs its course in the densest regions of the universe and nothing interrupts the process long enough to stop it. Alcyoneus is the largest scar, 16 million light-years of radio-emitting plasma, inflated by jets that carved through the intergalactic medium for tens of millions of years. The galaxy at the center is unremarkable. The black hole is not particularly massive, but the environment was right. The gas was thin enough. The jets stayed on long enough. And the result is a structure 4 times larger than IC 1000, 101's halo, a reminder that a galaxy's influence extends far beyond the region where its stars live. Porphyrion is the largest bridge, 23 million light-years from one end to the other. Jets that ran for 2 billion years, threading energy across the cosmic web, heating and magnetizing the space between galaxies, shaping the environment on scales so vast that the structure becomes part of the universe's architecture. It's not a galaxy in any traditional sense. It's a process, an event, a scar carved by a black hole that refused to stay quiet while the universe aged around it. 3 objects. 3 definitions of size, and no way to say which one is correct because they're all measuring something real. The largest galaxy is not a fixed thing. It's a question with 3 answers, and the answer you get depends on what you're willing to count. Stars, IC 1000, 101. Radio lobes, Porphyrion. The boundary where the galaxy's gravity gives way to the pull of the cluster around it. Somewhere in between, and the line keeps moving every time someone builds a better instrument. This is where scale stops being a number and starts being a problem. Not because the measurements are wrong, because the concept we're trying to measure has dissolved. A galaxy is not a thing with edges. It's a region where matter and energy are doing something interesting, and the extent of that region depends on what you're looking for and